Question belongs to digital logic design subject and was asked in GATE 1991. The topic name is circuits. So the question states, for the digital in figure, the expression for the output F is. So we need to find what is the expression for this output F. We have been given inputs A, B, X and Y. So this concept is basically based on CMOS and basically on logic gates using CMOS. So it's basically a standard architecture. So here what is happening is that when we are providing X and Y through here and A and B through here, then this F will behave like an AND gate. It will behave like an 4 input AND gate. 4 input AND gate. And the output would be just the product of all the input terms. It would be equal to X into Y into A into B. So the answer F is X, Y, A, B. This question belongs to computer organization subject and the topic name is memory organization. It was asked in GATE 1990. So the question states, in interleaved memory organization, consecutive words are stored in consecutive memory modules in which interleaving, whereas consecutive words are stored within the module in which interleaving. So let me first tell you what an interleaved memory organization means. Suppose we can have memory organization in two ways. We can have memory organization in two ways. First one is like this. Suppose we have RAM, so we will store the entire addresses like this. Suppose we have 256 million addresses. We want to generate 256 megabyte of memory and it is byte addressable. One word equals to 1 byte. So we need 256 million addresses over here. Bytes would be over here. And how many address bus size will we need? Address bus size is at 256 can be written as 2 to the power 8. So we need 2 to the power 28 because 256 is 2 to the power 8 and million is 2 to the power 20. So we need 28 address lines for address bus. This is a normal concept, but here the disadvantage is that when we have consecutive read and write operations, suppose we are reading from address 0, address 1, address 2, address 3, as we have locality of reference, so we will have consecutive reads and writes. So we will have consecutive reads over these addresses. And if we read from address 0 from a memory module, then there is some delay after which only we can perform another read or write. So between 0 and 1 there would be a delay, between 1 and 2 there would be a delay, between 2 and 3 there would be a delay. Now to solve this problem, we came up with this interleaved memory organization. So now I will explain you this interleaved memory organization. So what happens in this is, we will have different memory modules. Let us suppose we have 4 memory modules like this. We have 4 memory modules like this. So what was the total memory? 256 megabyte. It is equal to 2 to the power 28 bytes. So we will divide it equally into 4 parts. So here it would be 64 megabyte, here 64 megabyte, here also 64 megabyte, and here also 64 megabyte. And here what we will do is that we will have 64 megawords of size 1 byte. So how many bits of address lines we have? We have 28 address lines from A0 to A27, A26 and A27. So what we will do? For 64, how many do we need? For 64 megabyte, we need 2 to the power 6 and 2 to the power 20. We need 26 lines. So either we can have two options. In first case, either we will assign A0 to A25 for this selection. Like let us suppose assign A0 to A25 for selecting the address. It will go same over all the chips, and A26 and A27 will act as chip select. As we are using higher bits, so it is called high order. And in high order, what happens? Suppose we have address like this: A0, A1, A2, then we have A26, A27. So what happens? 0 to, as we have higher significant bit are changing, and it is same for this. For it will be 00 for all the 64 megabyte of this chip. So it will have address from 0 to 64 megabyte. It will have address from 64 megabyte to 128 megabyte. It will have address from 128 to 192 megabyte, and it will have address from 192 to 256 megabytes. So it will have addresses like this. Now what we are doing is that we will have another solution in. So the disadvantage of this is, if we are using consecutive memory addresses like from 0, 1, 2, 3 false, due to this delay, we need to have a delay between read and write. And here also, as we are selecting from the same memory module, delay would be there. So it is less preferred. And here 0, 1, 2, 3, all the addresses come in the same memory module. So consecutive words are stored in consecutive memory modules? No. Consecutive words are stored within the module. Consecutive words, 0th word, 1th word, 2th word, 3rd word, 4th word are stored in the same memory module in high order interleaving. Now we have another interleaving which I will explain you. It is called low order interleaving. So how it works is something like this. Let me explain it to you more clearly. Yeah. So we have addresses like this: A0, A1, A2, A3, and then A26 up to A27. So what we will do in low order interleaving, we will use A0 and A1, which means we will use least significant bit. These two bits for determining the chip select logic. They will determine the chip select logic. How it is determined previously also, and here also it is determined using 2x4 decoder. And these are used as address lines. These 26 bits are used as address lines. So how address will work? I will explain you this now. Suppose we have bits from A0, A1, A2 up to A27, A26. So we are changing this bit. This bit is fixed for each one. So what addresses will come in the first one? It will have all 00 for this, and all these will change, which means addresses like 0, 2, 0, 4, 8, 12 will come over here, as only this can change. So either this can be 0, then this can be 1, then we can have this, then we can have this, then we can have this, and addresses like 1, 3, 5, 7 will come over here, like 1, 1, 5, mod 4 would be there, 1, 5, 9, 13, and here it would be 2, 6, 10, 14. Here it would be 3, 7, then 11, 15, and so on. So consecutive addresses like 0, then 1 over here, then 2 over here, then 3 over here. Consecutive addresses will be stored in different modules. What is the advantage of this? The advantage of this is, if we are running a program and we are accessing addresses 0, 1, 2, 3, 4, 5, 6, 7, 8 due to locality of reference, then 0 would be over here, then it will go in some delay, but we can at the same time select 1 from here, then we can select 2 from here, 3 from here, and then again from the module 1 without any delay. So this is the advantage of this. So in low level, consecutive words are stored in consecutive memory modules in low order interleaving. So answer is, first fill in the blank is low order interleaving, and second one is high order interleaving. This question belongs to digital logic design topic. The topic name is number systems. It was asked in GATE 1991. So the question states, consider the number given by the decimal expression 16 cube into 9 plus 16 square into 7 plus 16 into 5 plus 3. The number of ones in the unsigned binary representation of the number is. So now, first of all, let me tell you a common formula. Suppose most of us are fond of these decimal numbers. So how will you evaluate this number? So you will evaluate it like you multiply it by 2 power 0, this by 2 power 1, this by 2 power 2, this by 2 power 3. So you have 1 into 2 power 3 plus 0 into 2 square plus 1 into 2 to the power 1 plus 1 into 2 power 0. If you have a general terms, like if you have a term, let us suppose a1, a2, a3, a4 with the base, let us suppose n, and you want to convert it. How will you convert it? You will do a1 into n4, a1 into n cube plus a2 into n square plus a3 into n power 1 plus a1 into n power 0, which means this can be converted directly to this. Now let us see this. How it is like? It is like 16 cube into 9 plus 16 square into 7 plus 16 power 1 into 5. We can write 3 as 16 power 0 into 3 as 16, anything to the power 0 is 1. So we can directly map this one to 9753 base 16. So we can convert, this is basically hexadecimal representation. To this is decimal, this one is decimal, and this one is hexadecimal. So we have converted decimal to hexadecimal. So we got this as hexadecimal. Now how do you convert hexadecimal to binary? You just write the binary equivalent of each of these numbers into 4 bits. So what's the binary equivalent of 1? 9, it is this. What's the binary equivalent of 7? It is 1110. What's the binary equivalent of 5? It's 0101. What's the binary equivalent of 3? It is 0011. This is 3, this is 5, this is 7, and this is 9. Now we are asked the number of ones in the unsigned binary representation. Unsigned means there would be no sign, which means 0 over here. Number of ones 1, 2, 3, 4, 5, 6, 7, 8, 9. So the answer is we have 9 ones. We just need to identify the pattern and convert it to hexadecimal and then convert it to binary. This question belongs to computer organization subject and was asked in GATE 1991, and the topic name is microprocessor. So the question states, using the 8087 arithmetic coprocessor with the 8086 CPU requires that the 8086 CPU is operated in which mode? So here we have 8087 arithmetic coprocessor. So this is a special type of processor, and we have 8086 CPU. So we are interfacing 8087 with 8086. So I will explain you this with the help of a diagram. So consider this. Here we have an 8086. This is the 8087 arithmetic microprocessor, and it is interfaced with either 8086 or 8088 CPU. So just remember these few points. The first point says that 8087 is an Intel microprocessor. So it is a processor with an architectural instruction set optimized for performing complex arithmetic operations. So it is used for complex arithmetic operations, and thus it is called arithmetic coprocessor. In 8087, along with the host microprocessor 8086, rather than serving the main processor itself, therefore it is referred to as coprocessor. So here 8087 do not serve as the main processor. 8086 is the main processor and 8087 is the coprocessor. So the third point states, an 8087 instruction can perform a given arithmetic computation 100 times faster than the equivalent 8086 instructions, which means 8087 is faster than 8086. So from here only we can easily see, as 8087 is faster, as we need to maintain the consistency, thus 8086 must be operated at its maximum speed. So which means it must be operated at its maximum speed or maximum mode. Now let us see further things. 8087 is an actual processor with its own specialized instruction set. So it has its own instruction set. Instructions for 8087 are written in the program as needed, interpressed with the 8087 instructions. And here, as 8086 fetches the instruction byte by byte from the memory and puts them in its queue, and 8087 also reads these instructions bytes by byte and puts in its queue. And 8087 decodes each instruction that comes to its queue. So it's 8086 queue and it's 8087 queue. And this is the most important point. And coprocessor 8087 is a coprocessor is connected to 8086, and as 8087 you can easily see an 8087 perform the instruction 100 times faster, thus 8086 must operate at its maximum mode. So the answer to this question is maximum mode. So the CPU is operated in maximum mode. This question belongs to Digital Logic Design subject and the topic name is Number Systems. It was asked in GATE 1991. So the question states, when two 4-bit numbers A equals to A3, A2, A1, A0 and B equals to B3, B2, B1, B0 are multiplied, then the bit C1 of the product is given by. So suppose we have two numbers A equals to A3, A2, A1, A0 and B equals to B3, B2, B1, B0 and we are multiplying it and we need to find the product, the first bit of the second bit of the product C1 of the product C. So suppose when we are multiplying 1, 3, 2 and 2, 1 in normal mathematics, then how we are doing it? 1 into 2, 2, 1 into 3, 3, 1 into 1, 1. And then we put a blank over here, then 2 into 2, 4, 2 into 3, 6, 2 into 1, 2. And then we add them up. 4 plus 3, 7, 1 plus 6 plus 1, 7, 2, 7, 7, 2. So we will do it similarly. So how we will do it? We will multiply A0 B0 A0 B0, then A1 B0 A1 B0, then A2 B0 A2 B0 A3 B0. Put a blank over here. Then A0 B1 A0 B1 A1 B1. Then we have A2 B1. Then we have A3 B1. Then we will put two blanks and multiply this by the entire above row A0 B2 A1 B2, then we have A2 B2, then we have A3 B2, then we will put three blanks, then we will multiply this by the entire upper row. We will have A0 B3, then A1 B3, then A2 B3, then A3 B3, then we will add them up. So this will give A0 B0, this will give A1 B0. We need to add them up. So what's the method to add them? So we will use the same method that we have used for half adder. Suppose we have two bits A and B. So here what are the two bits? Here the two bits are A1 B0 and A0 B1. And if we add them up, then carry is given by A into B and sum is given by A XOR B. So we need to use XOR in the sum. So we will get it like this. And for this one, we will have 3. So we will use full adder logic, full adder sum expression. But here only C1 is asked. So this is C0, this is C1 and C1 equals to XOR because the XOR, we are having XOR only in the half adder sum expression. So the answer is A1 B0 XOR A0 B1. This question belongs to programming subject and was asked in GATE 1991. The topic name is Pascal programming. So the question states, consider the following Pascal program segment. So this is a Pascal program. An appropriate loop invariant for the while loop is. So first let me tell you what is this loop invariant. Suppose loop invariant is a condition, any condition that is true in all three cases. First one is, let me write this over here so that you can refer it. A loop invariant is a condition that is true in these three cases: before start of loop, before, or we can say after each iteration, and the third one is after loop termination. In between it may become false or true, but at these three places it should always be true. Now let me first tell you what this program is doing. So it is first checking if I mod 2 equal to 0. Let us suppose we are having a number I. So either it can be 0 or it can't be 0. Its modulus can be 0, its modulus can't be 0. If its modulus is 0, modulus mod 2, let me write it like this, mod 2 is 0, is not equal to 0, which means this is odd number, which means this is odd number. So if it is odd number, then we are not even executing this. If it is even number, then we come in this while loop. Then what this while loop is doing? While loop, while the number is greater than equal to 0, it is dividing the number by 2. So suppose we have an odd number like 16. Then we divide it by 2. Then we get 8. Then we have if I mod 2. So what is this? What is this operation? This operation evaluates to true if LHS is not equal to RHS. Which means if I mod 2 is not equal to 0, then we will do this. If I mod 2 equal to 0, then we will do this. So here we have 8. 8 mod 2 equal to 0. No, it's not equal to 0. So we will do 8 minus 2. So I will become then 6. Then again we will come in the loop. While I is greater than equal to 0. Yes, it is true. 6 is greater than equal to 0. We will do 6 mod 2, 6 by 2, which means 3. So here we have 3. Then what we will do, we will again check if 3 mod 2 equal to 0 or not. 3 mod 2 is 1. It's not equal to 0. So we will do 3 minus 1. We will make it 2. So we will make 3 to 2. So this was before the start of the loop. Before the start of the loop, we have 16. And during the loop, we have 8 and we converted it to 6. Then we have 3 and we converted it to 2. Now we have 2. Then again we will come in the loop. Then what will happen? We will check 2 is greater than equal to 0. Yes. So what we will do? We will do 2 by 2, which means it will become 1. It will become 1 and then we will check 1 mod 2 equals 0. No. So we will make it 0. Which means this is during the third loop. We will have 2 to 1 to 0. During the second loop we have 6 to 3 to 2. And during the first loop we started with 16. We made it 8 and then ended with 6. Yeah. Then we have 0. Then we will again check while I is greater than equal to 0. Yes. So what we will do? Then again we will do I equals to I divided by 2, which means 0 by 2, which is 0 only. It will be 0 only. Then we will do I mod 2 equal to 0. Yes. So we will do I equals to I minus 2. We will make it minus 2. Then this while loop will fail. So we will come out over here. So what are the values? This is before the start of the loop. This is at the end of the loop. And what are after each execution? After first execution we had 6, after second execution 2, after third execution we have 0. If you analyze carefully, in the middle we may have an odd number or an even number. We can have an odd number or an even number. But at the end and in the starting, we will always have an odd number, which means I mod 2 is always equal to 0. This is the loop invariant. It may be false in between the loop, but before the beginning, at the end, or in the after each execution or before each execution, I mod 2 is always 0, or we can say I is always even. So this is the loop invariant, which means it is always true before the start of the loop, after termination, and before each iteration. So answer is I mod 2 equals to 0. This question belongs to algorithm subject and was asked in GATE 1991, and the topic name is sorting. So the question states the minimum number of comparisons, the minimum number required to sort 5 elements is. So suppose we have 5 elements. Let us suppose A1, A2, A3, A4 and A5. Here we are not being asked about the best case, as best case would be insertion sort, and for n items n minus 1 comparisons, as it would we will assume a sorted array, but here we need to take a general case. So let us suppose we have 5 items. So what are the ways of arranging these 5 items? We can have n factorial ways to arrange n items. So we will have 5 factorial ways to arrange these 5 items. So how will they look like? They will look A1, A2, A3, A4, A5, followed by A1, A2, A3, A5, A4, and so on like this. There would be some items, and then there would be some items in which A2 will come before A1, A2, A1. Here all A1 will be before A2. Then we will have some items A4, A5, A3, A5, A4, and there would be, so 5 factorial is 120. So as these are half half, so we will have 60 items like this and 60 items like this. So what happens in comparison based sorting? So we are basically comparing two items. So let us suppose we are comparing A1 and A2. Now there can be two cases. Either A1 is greater than A2 or A1 is less than A2. If A1 is less than A2, then we can discard this part, as out of these n factorial combinations, out of this 120 combination, only one combination will be our sorted answer. So we can discard this part if A1 is less than A2, as we can't have A2 before A1. And if A1 is greater than A2, then we can discard this part. So let us suppose we are discarding A1 is less than A2, so we are discarding second part. Now also over here, half of the items, now let us suppose we are making second comparison between A2 and A3. So out of the 60, 30 will have A2 before A3 and 30 will have A2 after A3. Let us suppose A2 is greater than A3, so we can discard this part. Which means at each one comparison, we are discards half possibilities. This is very important thing. As one comparison discarded 60 possibility, then another comparison discarded another 30 possibility, then another comparison will discard another 15 possibility, and so on. It will continue till we will reduce this n factorial possibilities to one possibility dividing by 2. So if we have n items and we reduce n items to 2 items, n items to 1 items by dividing by 2, then the number of steps equals to log n base 2. So here in this case, number of steps would be log n factorial base 2. And these are comparisons, so we will have an upper bound. So our answer is log n factorial upper bound base 2. So what is the value of n? N is 5. So log base 2 5 factorial upper bound. So we have log base to 120. What is 2 to the power 6? It's 64. What's 2 to the power 7? It's 128. So it would be something like 6.x upper bound. Sorry. What's 5 factorial? 5 factorial is 5 into 4 into 3 into 2 into 1. 20, 3 is 60, 62, 120. Now let us see. What is 2 power 6? It's 2 to the 4 to the 8, 16, 24, 32. What's 2 to the power 7? It's 64. What's 2 to the power 8? It's 128. So we can easily see it would be 6.x upper bound. So we can write it 7. So we need 7 comparisons, minimum comparison to sort 5 items. So answer is 7. This question belongs to algorithm subject and was asked in GATE 1991, and the topic name is binary trees. So the question states the weighted external path length of a binary tree in the given figure is. So we have been given a binary tree. What is a binary tree? A tree which can have at max 2 nodes, which means it can have 0 node, 1 node or 2 node. Each node can have either 0 node, 1 node or 2 node, at max 2 nodes. So we need to find the weighted external path length. All these are nodes. This is node, this is a node, this is a node, this is a node, this is a node. The circles are internal nodes, and the square boxes are external, or we can say leaf nodes. So we have internal node and external node. All these are leaf nodes. So external path length, the weighted external path length is calculated for the external node, which means the leaf node, and it is equals to, we will span through all the nodes, and what we will do, we will just multiply the weight of the node with the path length. So what's the path length of the node? So I will give you the definition for path length. Path length means number of edges from root to given node. So if we are over here, then the path length of this node 15 is 1, as we have 1 edge from root to this. Path length of this 10 is 1, 2 and 3. So we will calculate weighted external path length. First, let's calculate for this node 2. What is its path length? 1, 2, 3, 4. 4 is the path length, weight is 2. For this one, 4 is the path length, weight is 4. For this one, 4 is the path length, weight is 5. For this one, 4 is the path length, weight is 7. For this one, 3 is the path length, weight is 9. For this one, 3 is the path length, weight is 10. For this one, 1 is the path length, weight is 15. If you will calculate this, it would be 4 to the 8, 4 4 60, 4 5 20, 7 4 28, 9 3 27, 3 10 30, 1 5 15. So it will be equal to 144. So the answer is weighted external path length is 144. This question belongs to algorithm subject and was asked in GATE 1991. So the question states, if the binary tree in figure is traversed in order, then the order in which nodes will be visited is. So we need to just give the in order traversal for the given tree. So what is in order traversal? There are basically three types of traversal: in order traversal, pre-order traversal, and post-order traversal. Suppose we need to give in order traversal for a node n. Let us suppose a node n. So how it works? First we go to the left subtree, which means first we will find the in order traversal of left of n. Then we will print our n, and then again we will find the in order for right of n. This is the code. This is the recursive code for finding the in order. Now let me tell you the shortcut for this. If you go by this code, then also you can find. Suppose we will start at root. In order means first we will go to the left subtree, then we will come to the root, and then we will go to the right subtree. Let me write it like this. Suppose we are finding at a node n, then first we will go to the left side, then to the node, and then to the right, which means left, node, right. So first we will go to the left. Okay. After coming over here, first we will go to the, then again we will see this, and we will go to the left. After coming over here, here we will have a terminating condition. If n equals to null, then we will return. So we will come over here. First, then again we will see this. We will go to left. Left is null, we will return. Then node, which means 4 will be printed. Then we will go to right. Right is null. So again we will return. Then when we will come over here. So we went to left and completed it. Now we will print this one. Then we will go to right. Again over here, the same thing. Left, it's null. Then node will be printed. Then right, it's null. So this right subtree is also completed. So for this subtree, for one, left is completed, node is completed, right is completed. So now we will come to 7. For 7, left is done. So now 7 will be printed. Then we will go to right. For this one, left is null. So then we will print the node and go to right. For this one, left, first we will go, then we will, here its left is null, node we will print, then we will go to right, right is null. Then we will come over here. Its left is done, node is done, then we will go to right. For 8, left is null, then we will print node, we will go to right, it's null. Then we will come back. Then we will come back, then we will come back. So how it is printed? First we go over here, left, node, then right, then over here, node, then over here, right, then first left, then node, then we come over here, then left, node, right. So in order traversal is this 41673258. So it's 41673258. This question belongs to programming subject and was asked in GATE 1991, and the topic name is recursion. So the question states, consider the following recursive definition of fib. So we have a fib function. So it's basically a Fibonacci function, you can easily see from the logic. So we have a Fibonacci function. There is no need to remember this, but I am telling you. So what it is doing, if n is 0, then it returns 1. If n is 1, then it returns 1. else it returns Fibonacci of n minus 1 plus Fibonacci of n minus 2. So it is asking the number of times fib is called, including the first call for the evaluation of fib of 7. So let me tell you how we can do this. Suppose, let me dry run this for you for a smaller input like fib of 3. So if n is 0, no. Then what we are doing, we are calling fib of 2 and we are calling fib of 3 minus 2 is 1. Then for fib of 2, we are calling fib of 1 and fib of 0. And for fib of 1, we are just returning 1. So number of time fib is called 1, 2, 3, 4, 5. Including the initial call means this is also including. If it was excluding, then answer will be 4, and including answer is 5, as we also include this. So we can easily do this very easily by the recursive functions. Let us suppose t of n gives the number of calls, it is number of fib calls for n. So what it is doing, here there is no call, here there is no call, there is one call for this. For this fib, there is one call. So we do 1 plus. Then we are doing fib of n minus 1, fib of n minus 2, which means the number of calls for this will be evaluated by this, and the number of calls for fib of n minus 2 will be evaluated by t of n minus 2. So it will give us the total number of calls. So it is, what is this? It is recurrence relation for, it is recurrence relation for number of fib calls. We can write recurrence relation for anything, not just for the time complexity. We can write recurrence relation for anything we want to. It's a myth that we can only write it for time complexity. Now what will be the base cases? So what is the value of fib of 0? Number of recurrence calls for 0. One recurrence call for this function only. Then it is just returning. So it is only 1. What is fib of 1? Fib of 1 is 1 for this function, and then it's just returning by this. So it's 1 only. So what is fib of 2? For fib of 2, we can use our recurrence relation, which is this. So fib of 2 is 1 plus fib of 2 minus 1 is 1, 2 minus 2 is 0, which means fib of 1 plus fib of 0, 1 plus 1 plus 1, which is 3. What are the number of fib calls for fib of 3? It's fib of 2 plus fib of 1 plus 1, 3 plus 1, 4 plus 1, 5, which means it is equal to 1 plus its previous two calls, 5 plus 3, 8 plus 1, 9. So fib of 5 equals to 9 plus 5, 14 plus 1, 15. Fib of 6 equals to 15 plus 9, 24 plus 1, 25. Fib of 7 equals to 25 plus 15, 40 plus 1, 41. So answer is 41 fib calls. So you can easily do this by writing the recurrence relation. So answer is 41. This question belongs to compiler design subject and was asked in GATE CSE 1991. So the question states, the arithmetic expression a plus b into c minus d divided by e whole power n is to be evaluated on a two-address machine where each operand is either a register or a memory location with a minimum number of memory access of operands. The number of registers required to evaluate this expression is, the number of memory access of operands is. So we have been given an expression and we have been provided with the information that we are having two address machine. Two address machine means we will be having two addresses, either it can be register address or memory address, in which each operand is either a register or a memory location. We need to find the number of registers required to evaluate this expression and the number of memory access of operands in the case where it should be minimum. We should be having the minimum memory accesses. So for this there is some preliminaries assumptions. Let me tell you those. So we will assume that every ALU instruction is of the form, like it will have opcode, it will have operand 1 and operand 2. So what we will assume? We will assume that every ALU instruction, which is a data manipulation instruction, is such that the first address of the instruction is the destination. It will serve two purposes. It will serve the destination purpose as well as the opcode 1 purpose. It will serve as the destination as well as the address of the first operand, and it is the address of the second operand. Sorry, it's operand not opcode. Operand 1 and operand 2. There is some confusion. These are operands and this is opcode. So we have operand 1. Suppose we have something like add R1 followed by R2. So this means that we will get the value from register R1 and then we will get the value from register R2. We will add them, and register R1 is the destination which will store the sum R1 plus R2. And here this double star is equals to exponentiation. Exponentiation. Exponentiation means power. So here, as this is a 2 address machine, we have been given that this is a 2 address machine where each opcode is either a register or a memory location. So what are our priorities? First priority is we are given a minimum number of memory access. So we will have minimum memory access. And what is our second priority? Second priority is this. The number of registers, we need to find the number of registers and it should be minimum registers. So these are our priorities. Now let us see how we will do this. So I will tell you each operation that we need to do to evaluate this expression. So let me first write this expression so it becomes more clearer to a plus b whole star c minus d divided by e star star l. So I will write the operations and tell you the number of registers and the memory access. I will tell you over here. So first what will happen is that we will first of all bring the value a, this a into register R1. So we have a one memory access. So one memory access is done. Okay. Now what we will do? Then we will do add R1 comma B. So what it will do? It will sum the value of R1 and with the value B. So R1 is A. So we will do A plus B and it would be stored in register R1. So we have used the register R1. And we have second memory access here for this B. So we have the second memory access for B. Let me write. We have memory accesses for what things? We have memory access for A. Then we had a memory access for B. Then what we will do? We will then do multiply R1 with C. So what R1 has? R1 has A plus B. So we will multiply it with C and store it in R1. So this is the current value of R1. And what are the memory access? We have a memory access for C and we haven't used any extra register. It's R1 only. Now R1 has A plus B into C. Now what we will do? We will bring into the register R2 the value E. So we have a memory access for E and we have used another register R2. Now what we will do? We will do exponent R2 with L. So we have a memory access for L. We haven't used any extra register. And what we have done over here? We have done R2 will here R2 will store R2, the value of R2 which is E power L. So which is equals to E double star L. So this is the contents of R2. Now what we will do? We will bring into the register R3 the value of D. So we have a memory access for D and we have a register R3. Now what we will do? As here D is the first operand, we will bring it into the register because first address in the instruction is destination as well as the address first operand. Thus we will bring R3 first. Then what we will do? We will do divide R3 by R2. So what we will do? R3 equals to R3 divided by R2. So we will have R3 equals to what is the value of R3? R3 has D divided by R2. What is value of R2? E whole power L. So do we have a memory access? No. Do we have an extra register? No. These are capital R's. Now what we will do? We will do subtract. So we have both these things. Now what we will do? We will do subtract R1 and R3 and store it in R1. So R1 has this, R3 has this. We will do hold this and store it in R1. Do we have a memory access? No. Do we have an extra register? No. And we got our answer. So we have used 3 registers and 1, 2, 3, 4, 5, 6 memory access. So the answer is we will be using the number of registers is 3 and number of memory accesses are 6. This question belongs to compiler design subject. It was asked in GATE 1991 and the topic name is precedence graphs. So the question states, a given set of processes can be implemented by using pair begin and parent statement if the precedence graph of these processes is. So if we have a set of processes, then we can just write pair begin and parent at the end, and we can write the processes over here. This pair begin and parent is basically you refer to this parallel begin and parallel end, which means all the processes in this can execute parallelly. P1 and P2 can execute parallelly. So here for this, you can refer to this link. I will show you what's there in this link. You can refer to this and you will get to know the complete document regarding this. Let me show you the link first. The link says one of the limits on using pair begin and parent and any related constructs is that the program involved must be properly nested. So the program must be properly nested. So properly nested is the answer to that question. And it says not all programs are. For example, here you can see if it is possible, we must determine if the above program is properly nested. If not, we cannot represent it with pair begin and parent, which require a block structure and hence proper nesting. So which means it should be having properly nested is the correct answer to this question. For pair begin and parent, we should have proper nesting. This question belongs to engineering mathematics subject and was asked in GATE 1991 and the topic name is linear algebra. So the question states the number of integer triplets I, j and k with I, j and k greater than equal to 1 and less than equal to 300 such that I plus j plus k is divisible by 3 is. So we have two methods of doing this. I will be telling you both these methods, you can follow any of them. So what the question is asking? The question is telling us we need to find the values of I, j and k such that I plus j plus k is divisible by 3, or we can say I plus j plus k mod 3 equal to 0. Such that we have this constraint over I, j and k. I, j and k is greater than equal to 1 and less than equal to 300. So let us suppose how many values can we have for I and j. First of all, let us think it like this. For I we can have 300 values. For j we can have 300 values. How many pairs of I and j we can have? We can have 300 into 300 pairs of I and j. Like we can have any value 1, 1, 1, 2, 1, 3, 1, 4, 1, 300, 2, 1, 2, 2, 2, 3 up to 300, 3, 1, 3, 2, 3, 3 up to 100. And suppose here 2, 2, the value of I to be 2 and j to be 2 will be considered different than the value, like we will have something like this now 1, 2, 3, 300. Then we will have 1, 2, 3, 300. So 1 can be mapped to anything and then 2 can be mapped to anything. So which means 1, 2 and let us suppose we have 3 and 3 over here, and 2, 1, 3 would be different as these are triplets. So we will have 300 into 300 combinations for I and j. And for any combination, let us take any combination, I to be 5, j to be 3. So 5 plus 3 is 8. So k can be 1 as 5 plus 3 plus 1, 8 plus 1, 9. 9 mod 3 equals to 0. Or we can have 4, we can have 7, we can have 10. So it is equal to 300 by 3 as we have how many factors, how many numbers from 1 to 300 are divisible by 3. It is equal to 300 by 300. So here we can have 100 combination. And let us suppose any other pair for I to be 5, I to be 2 and j to be 2. Okay, then how many can we have? 4. We can have k to be 2, k to be 5, k to be 8, k to be 9 as 9, 10, 11, 12, 4 plus 9. Wait, to 4 to 6, or we can have 5, 5, 6, 7, 8, 9, or we can have 8, 8, 9, 10, 11, 12, or we can have 11, 11, 12, 13, 14, 15. So here also we will have 100 combination. So for each pair we have 100 combination for each pair, 100 per pair. And we have 300 into 300 pairs. So the number of combinations are 300 into 300 into 100, which is 9 into 10 to the power 6. Let me tell you the second method. For second method, let us suppose we need to find I plus j plus k mod 3 should be equal to 0, which means either what can be the values of I mod 3, j mod 3 and k mod 3. The sum mod 3 equals to 0 when their modulus sums are equal to 0, which means either we will have 0, 0 and 0 as 0 plus 0 plus 0 is divisible by 3, or we will have, let us suppose we have x mod 3. What can be the value of this? We can have 0, 1 or 2, as x mod n can have numbers from 0 to n minus 1. So x mod 3 can have values from 0, 1, 2, and only those values will come in this answer which have their sum divisible by 3. So we will have 0, 0, 0, or we will have something like 0, 1 or 2, or we can have 0, 2 or 1, we can have 1, 2, 0, we can have 2, 1, 0, we can have 1, 2, 0, we can have 2, 0, 1, we can have 1, 1, 1, and we can have 2, 2, 2. Now you tell me, how many pairs are divisible by 3 such that they give the remainder 0? There are only 100 pairs. There are 1, there are 3, 6, 9 up to 300. And there are 100 pairs. So we have 100 pairs for this. And how many pairs gives the modulus 1? So there are 4, 5, 6, 7, 8, 9, 10. There are also 100 pairs of this. 100 pairs of this and 100 pairs for this, like we can have 1 no mod 3 equal to modulus equals to 2, so we can have numbers like 5, 6, 7, 8, 9, 10, 11. So there are also 100 numbers. For each we have 100 numbers. So a pair will be equal to 100 into 100 into 100 combinations for a pair. And how many pairs do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. And we have 9 pairs. So the answer is 9 into 10 to the power 6. So both are giving 9 into 10 to the power 6. So the answer is 9 into 10 to the power 6. This question belongs to the topic subject engineering mathematics and was asked in GATE 1991. And the topic name is set theory. So the question states, if the longest chain in a partial order is of length n, then the partial order can be written as dash of antichains. So let me tell you what is an antichain. A subset A of S. We have a set S and we have A as a subset of S. It is called an antichain if no two elements in A is antichain. If no two elements in A are comparable. Okay. Now here what it is given, we have a longest chain in a partial order is of length n. So we have a chain of length n, 1, 2, 3, n. Now if we take a total ordered poset Z on less than equal to containing n elements from 1 to n, then we know every element is comparable to every other element. Yes, every element will be comparable to every other element, and if we take any two of these n, then they will also be comparable. Any two will be comparable, we can compare those two. So we take at most one element in a subset A. As in A, no two elements in A should be comparable, but every element will be comparable in a partial order. So we will take at most one element in a subset A. So the total number of subsets would be n, as each item will come in a separate subset. So we will have n subsets. So basically in a poset, not in a toset, basically in a poset not in totally order, having a chain of length n, no two of these n elements can go to the same subset, otherwise it won't be anti-chain, because no two elements in a subset is comparable is a condition for anti-chain. So no two of them should go to the same subset, as if they belong to the same subset, then these two will be comparable and hence they won't form an anti-chain. So at least we will have n different subsets and each subset will have one item. So hence the answer is, if a longest chain of partial order is of length n, then the partial order can be written as a partition of n antichains, and these are disjoint antichains, as each item will go into one antichain. So the answer is partition of n disjoint antichains. This question belongs to the subject engineering mathematics. It was asked in GATE 1991 and the topic name is graph theory. So the question states, the maximum number of possible edges in an undirected graph with n vertices and k components is. So what is a component? Component. A component is basically a connected subgraph. Connected subgraph. So if we have two components, which means they shouldn't be connected. Intercomponent shouldn't be connected. So we need to find the maximum number of edges. So suppose we have only one component. Then what is, in which condition do we have maximum edges? When it is a complete graph, or we can say a complete component. A complete component has maximum number of edges in case of a single graph. Now here we are given that we have k components. Let us suppose it is component 1, component 2, component 3 up to till component k. So as we want to find out the maximum number of edges, and the maximum number of edges is when it is complete, and the formula for complete is nc2, or we can write n into n minus 1 by 2. So we will get maximum number of edges when we have maximum vertices in one component. So we will do a greedy approach. We will give one vertex to each component. So each first k minus 1 component, each with one vertex, will have k minus 1 vertices. Let me write k minus 1 and ck. So all of them will have one vertex. So total vertex use are k minus 1. So number of vertices left are n minus k minus 1. Or we can write it to be n minus k plus 1. As we do not have the edges between two components, so thus there can be no edges between any two component. But intercomponent, we can have edges, but with one vertex we can't have any edge. So we have 0 edge over here, 0 edge over here, 0 edge over here, 0 edge over here. But with these many vertices, how many edges do we have? We have n minus k plus 1 c2 edge, which is equals to n minus k into n minus k plus 1 by 2 edges, as we want to make this component as complete component. So the gist of this problem is, if we have k components, we couldn't have the edges between components, thus we will apply greedy approach and give one vertex to each k minus 1 component and give the rest vertices to the last component and make it a complete component by connecting all the vertices. Like if we have 4 vertex, we will make it complete by connecting all the vertices. And the formula is nc2. So we will get n minus k plus 1 c2, and it is equal to this. So the answer is n minus k into n minus k plus 1 divided by 2. This question belongs to Digital Logic Design System subject and was asked in GATE 1991. So the question states, match the pairs in the following questions by writing the corresponding letters only. So it is a match the following question. So it has some IEEE standard formats like IEEE 488, IEEE 796, IEEE 696 and RS-232C, and we need to match it to specifies the interface for connecting a single device, specifies the bus standard for connecting a computer to other devices including CPUs, specifies the standard for an instrumentation bus, and specifies the bus standard for backplane bus called multibus. So it's basically, you need to just remember these standards. There is no logic behind it, just these are basic standards. It's better to remember them. So I have provided the link from where I have got this information, and here you can refer by going to this link, and this is just a Wikipedia information. So here you can see over this link that IEEE 488 is a short-range digital communications 8-bit parallel multi-master interface bus specification developed by HP. It subsequently became the subject of several standards and is generally known as general purpose interface bus. So A is basically mapped to option R. It's basically mapped to option R, specifies the standard for an instrumentation bus. Now let us see option B, IEEE 796. So the IEEE 796 bus was developed by Intel in 1974 and is called multibus. In 1978, the first IEEE working group meeting dealt with the issues. There were some issues in IEEE 796. They were resolved to make multibus a suitable general acceptable standard. So it specifies the standard for backplane bus called multibus. So option S is true. Now IEEE 696. So IEEE 696 specifies the applies to interface system for computer system components interconnected by a way of 100 line parallel backplane, commonly called as S100 bus. So it's basically used for connecting a single device. So it's option B. Now let us see RS-232C. So it is a long established standard. C is the current version that describes the physical interface and protocol for relatively low speed serial data communication between computer and related devices. So it specifies the bus standard for connecting a computer to other devices including CPU. So it's mapped to option Q. You can also see these RS-232Cs in our modern computers. So the mapping is RSPQ. This question belongs to Digital Logic Design subject and was asked in GATE 1991. So the question states, match the pairs in the following questions by writing the corresponding letters only. So for the 8086 microprocessor, so we have 8086 microprocessor. So these are various pins or the modes. So we need to tell which pin is used for what. We have RQ/GT, log, hold and ready. And the functionalities are used by processor for holding the bus for consecutive instruction cycle, used for extending the memory or IO cycle times, used for getting hold of processor bus in the minimum bus mode, used for requesting processor bus in the minimum bus mode. So basically for this you need to know the 8086 architecture. So this is the architecture for 8086. So here we have in minimum mode we have hold, we have RQ/GT 0 and 1, and then we have this ready, and then over here we have the lock. So here are the 4 pins. So their working is something like this. So RQ/GT, it is basically RQ stands for request and GT stands for grant. So these signals are used by other processor requesting the CPU to release the system bus. When the signal is received by CPU, then it sends an acknowledgement. RQ/GT0 is higher priority than RQ/GT1. So it's basically used by processor for holding the bus for consecutive instruction cycles. So it's basically mapped to option P. And what is log? So when this signal is active, it indicates to the other processor not to ask the CPU to leave the system bus, which means CPU will get hold of the system bus. It is activated using the log prefix or any other instruction and is available at pin 29. So it's basically used for extending the memory or IO cycle time. As here we won't be releasing the bus. Now we have option C, hold. So hold, this signal indicates the processor that external devices are requesting to access the address or data bus. So it's basically used for requesting processor bus in minimum bus mode. So we have option S over here. Then we have ready. So it's an acknowledgement sent from IO devices that the data is transferred. It is an active high signal. You can see ready is an active high signal over here. It's active high. When it is high, it indicates that the device is ready to transfer the data. When it is low, it indicates wait state. So it's basically used for getting hold of processor bus in minimum bus mode. So we have option R. So the correct mapping is P, Q, S and R. This question belongs to operating system subject and was asked in GATE 1991. So the question states, match the pairs in the following questions by writing the corresponding letters only. So list A contains, list 1 contains body system, interpretation, pointer data type and virtual memory. And list 2 contains runtime specification, segmentation, memory allocation and garbage collection. Let me tell you each of them one by one. So what is a buddy system? Buddy system is used for memory allocation. Suppose we have a process list coming, like we have a process of size 50K, we have a process of size 20K, we have a process of size 10K, we have a process of size 13K. So how do we allocate memory? So in buddy system, we keep memory as a complete block. So let us suppose it's 100K. Now when a new memory comes, we at runtime only we divide it into half part. So we have 50K and 50K. And then we start allocating from bottom part. So 50K is allocated over here. Then 20K comes. So again we divide it into two parts of 25K and 25K. Then again we try to divide it of 12.5K and 12.5K. But 20K won't come over here. So we don't divide it in that case. We will keep it like this. and put our 20k over here. 20k will come over here and this will get wasted. Then we have 10k. So we will try to divide it 25k into two halves, 12.5k and 12.5k, and put 10k over here and 2.5k will get wasted. Now 13k can't be allotted. So we are basically dividing at runtime. So buddy system is basically used for memory allocation. And we can also have runtime specifications. We can have option P as well as option R for this. Now let us see if we are able to resolve the contradiction or not. Let us see other options. Interpretation. So there are basically two terms, compilation and interpretation. So suppose we are converting our high level language to machine language or zeros or ones. So in compilation, we convert the entire code at once into zeros and ones using compiler as our program. And in interpretation, we scan the lines one by one of a program and convert each of the lines into its equivalent machine code and check for the error. So it's basically done at runtime. So interpretation is basically mapped to runtime, which is option P. So here we can easily see that B is mapped to option P, so A is mapped to option R. Memory allocation. Now we have pointer data type. So what is a pointer data type? Pointer is nothing but pointer is a variable which is basically used to store address of another variable. Let us suppose we have a variable PTR. It is a pointer variable and it stores address of a variable A which has address 1000. Pointer has address 2000. It has value 10. If PTR stores at value 1000, then A is a normal variable, and it is a pointer variable. So pointer variable. So what happens during garbage collection? Suppose this is dynamic memory allocation. It occurs in heap. At runtime, we are doing dynamic memory allocation. Suppose we are creating nodes for linked list. So the memory will be allotted in heap. Suppose we are creating nodes and creating. But there are some languages like Java and C++ in which there are garbage collectors. So how these garbage collectors work is that how will they come to know like they had to remove a node or not? Like it might be possible that we are using a node. So they will remove a node in the case when there is no pointer pointing to that node. So pointer can be basically used for garbage collection. So C is mapped to option S. Now we have virtual memory. So I will explain you this concept with the help of a diagram. So refer to this diagram. So what is a virtual memory? Suppose nowadays you can see we have 10 GB of games, 20 GB of games, and when we want to run a program we need to bring it to our RAM. But nowadays mostly we are using 4 GB RAM or generally 8 GB RAM. So we can't bring the entire program, so we divide it into different parts. In segmentation we divide it into different segments. So this is our logical address space, or we can say virtual memory. Virtual memory means we assume that it can be occupied entirely in the RAM, but it's not the case. Here we divide our virtual memory into segments, and these segments will be brought to main memory. And the logical address space to physical address space mapping can be done with the help of segment table. Here we have segment number and offset. So using, and the address of this is present in segment table base register, which is a register of our processor. So virtual memory is basically, why is it used? It is used for segmentation. So option Q. So correct mapping is R, P, S and Q. This question belongs to algorithm subject and was asked in GATE 1991. So the question states, match the pairs in the following questions by writing the corresponding letters only. The number of distinct binary trees with n nodes, the number of binary strings of length 2n with the equal number of zeros and ones, the number of even permutation of n objects, the number of binary strings of length 6n which are palindromes with 2n zeros. And the options are n factorial by 2, 3n cn, 2n cn and 1 upon n plus 1, 2n cn. So let me tell you first what is the meaning of this x and r. So it is equivalent to xcr. Okay, it is equivalent to x factorial upon r factorial into x minus r factorial, which means choosing r out of x items. Okay, now let us see all the options. So it's basically a standard question. So here we will be given n nodes and we need to find out how many distinct binary trees we can construct. So it is equal to nth Catalan number. It is a standard problem, Catalan number. And what is nth Catalan number? It is equal to 2n Cn upon n plus 1. Or we can write 2n Cn upon n plus 1. So the correct answer is option S. So A is mapped to S. Now let us see option B. It's an interesting question. So the question states the number of binary strings of length 2n with an equal number of zeros and ones. So we have a length 2n. So we need to fill it with n zeros and n ones. Okay, as both are equal. So what we can do, we can just select n positions, which can be done by 2n Cn. We will select n position, we will get those n positions. And in those n positions, we can either put 0. And if we put 0 in all those n positions, then rest position will have 1. So we just need to select n positions and put either 0 or 1 in those positions. So answer is 2n Cn, or we can write it like this, 2n Cn. So its mapping is R. Now let us see option C. So what option C says? Option C says n number of even permutation for n objects. So we have n objects. Let us suppose we have 1, 2 and 3. 1, 2 and 3. So what is an even permutation and what is an odd permutation? So let me take a bigger example so that you get it more easily. Yeah. So what is an even permutation? So an even permutation is a permutation that has even number of two element swaps. So let me tell you the meaning of this. Suppose this is our number. So how many permutations will it have? It will have 4 factorial permutation, 24 permutation. So one of its permutation will be 1, 2, 3 and 4. So how many swaps do we need to do from coming over here to here? 0 swaps. Then another permutation we have 2, 1, 3, 4. How many swaps do we need to do from coming from here to here? Just one element swap, 2 and 1. So we have one swap. Now we will have some items like we can have 3, 1, 2, 4. So how many swaps do we need to do? First we need to do 2 and 1 swap, come over here. Then we need to do 3 and 2 swaps and come over here. So we have 2 swaps. So we need to find the even permutation, number of even permutation. Number of even permutation means even number of swaps. Even number of swaps means 0 swap, 2 swap, 4 swap, 6 swaps. So this will come under even swap, this will come under even swap, this will come under odd swap. As even and odd both will be equal, so how many permutations are there? We have n factorial permutations. Number of even permutation will be n factorial by 2 and number of odd permutation will be n factorial by 2. So answer is option B. Even and odd permutation both will be equal. Now let us see the option D. Option D states the number of binary strings of length 6n. So we have a length 6n. We need to find number of binary strings, which means it will have only zeros and ones, which are palindromes with 2 and 0. So what is a palindrome? A palindrome is something like let us suppose RAXAR. Palindrome means it's readable same from left to right and right to left. Okay, of the form WW reverse or WCW reverse. But as we have 6n as 6n will always be an even number. So WCW reverse will not happen. We will have WW reverse. So which means first 3n items will be same as the last 3n items. It will be just the reverse. So we are basically focused on just these 3n items. We can neglect them as of now. So as it is a palindrome and it means it should have 2 and zeros. So if it has some 0 over here, then those zeros will also be over here. So we can reduce the problem to length 3n with n zeros. As if we have n zeros over here, then n zeros will be over here. So in how many ways can we figure out n positions out of 3n positions. It can be done in 3n Cn. So in 3n Cn, what we will do? We will find out those n position out of these 3n position, fill it with zeros. Let us suppose we fill some position with zeros. Now rest 2n position we will fill with 1. And we will do reverse of this to get the palindrome over here. So this can be done in 3n Cn. So answer is option Q. The correct mapping is S, R, P and Q. So this question belongs to computer organization subject and was asked in GATE 1991. So the question states, choose the correct alternatives, more than one may be correct, and write the corresponding letters only. The advantages of CMOS technology over MOS technology is lower power dissipation, greater speed, smaller chip size, fewer masks for fabrication, and none of the above. So what is a CMOS technology? So here is a diagram for it. So CMOS stand for complementary metal oxide semiconductor. So it's basically a technology which is used for creating the semiconductors, or we can say MOSFETs. So we have one complementary metal oxide semiconductor and another one we have the normal metal oxide semiconductor. So this is the diagram for it. It's basically a fusion of NMOS and PMOS. So we have certain advantages of using the complementary metal oxide semiconductor. I will write them over here. First one is low static power consumption. Second one is less complex circuit. Third one is high density of logic functions on chip. Then we have low static power consumption, it's already done. Then we have high noise immunity. So what are the options? Fewer masks of fabrication? No, as we have higher density. Smaller chip size? No. Greater speed? No. We have low power dissipation, very low static power consumption or dissipation in case of CMOS. So the answer is option A. This question belongs to the subject Digital Logic Design and was asked in GATE 1991. And the topic name is Sequential Circuits. So the question states, choose the correct alternatives, more than one may be correct, and write the corresponding letters only. Advantage of synchronous sequential circuits over asynchronous ones is faster operation, ease of avoiding problems due to hazards, lower hardware requirement, and better noise immunity. Or we have option E, none of the above. So here, what are synchronous circuits and what are asynchronous circuits? In synchronous circuits, we have the same clock pulse in every flip-flop. But in asynchronous circuits, the output of one flip-flop may serve as a clock for another flip-flop. Thus, in synchronous circuits, all the output will change at the same time, and asynchronous circuits are unpredictable. So for this, refer to these statements. So what option A states? It is asking synchronous sequential circuits over asynchronous one. What are the advantage? Faster operation. So see, says this. In asynchronous circuits, there is no clock, and the state of circuit changes as soon as the input changes. Since they do not have to wait for clock pulse, as there is no clock, we do not have to wait for the clock to begin processing inputs. Asynchronous circuits can be faster than synchronous circuits, and their speed is theoretically limited by the propagation delay of the logic gates. The flip-flops are made of logic gates, thus, due to the absence of clock, they can begin processing the input as soon as they want to with the delay of the clocks only. Thus, this option is false. Synchronous do not have faster operation, asynchronous have faster operation. Let us see option B. So option B is saying ease of avoiding problems due to hazards. But option B is true. Like synchronous circuits can easily avoid the hazards because if transition on two inputs arrive at the same time. Like if transition on two inputs arrive at the same time in synchronous circuits, the circuits can go in wrong state depending on slight differences in the propagation delay of the gates. This is called race condition or hazard situation. In synchronous circuits, this problem is less severe because race condition can only occur due to inputs from outside the synchronous system. Thus, synchronous circuits have less severe hazard problem. And you can refer to this link for this given statement. This statement has been taken from this Wikipedia link. So option B is true. We can easily avoid hazards in the synchronous circuits. Option C. Option C is false because of this above statement only. Because if we don't consider how to avoid hazards in the asynchronous circuits, thus option C is true, false. Like lower hardware requirement is not there in the synchronous circuits. Option D. Better noise immunity. So you can refer to this paper. This paper is regarding the behavioral transformation to increase noise immunity in asynchronous specifications. So option D is false as better noise immunity is not an advantage of synchronous sequential circuits. You can see this statement. This statement is taken from the paper. So this statement says asynchronous circuits seem to have good candidate to alleviate the problems originated by simultaneous switching noise, which means asynchronous circuits are used to avoid this noise problem, which means synchronous have this noise immunity problem. However, they are also more sensitive than synchronous ones to spurious signal transition and delay variation produced by crosstalk noise. You just refer to this statement. It's a good candidate to alleviate the problems originated by simultaneous switching noise. Thus, synchronous do not have better noise immunity. And option E is also false, none of the above. So answer is option B. This question belongs to the subject operating systems and was asked in GATE 1991. And the topic name is virtual memory. So the question states, choose the correct alternatives and write the corresponding letters only. The size of address space in virtual memory system is limited by the size of MAR, the available secondary storage, the available main memory, all of the above, none of the above, or both A and B. So let me tell you the concept behind this. So what happens is that we have our hard disk, or we can say secondary memory, and we have our main memory, or we can say RAM or main memory. Okay. Then we have a CPU. What CPU does? CPU generates the logical address. Logical address, which is converted to physical address. Physical address, and then it is searched over here. And where this logical address is stored? This logical address is stored in memory address register, or we can say MAR. Now what happens? So nowadays, what is the size of RAM that we are seeing in our laptops or computers? It is 16 GB or 32 GB. And what are the size of softwares that we are seeing? Or we can say the programs or softwares. So we can see hundreds of GB of games or larger software, 50 GB softwares, games, all these are present. Videos are over 1 GB. So we can see these sizes are definitely greater than RAM. So when we want to run a program, we need to bring it to the RAM. But if the size is like, and what is the size of secondary memory? It's in TBs, like 1024 GBs, 1024 GBs. So basically, all these programs need to be in secondary memory only. So secondary memory size should be definitely greater than this. So the size of address space in a virtual memory system is limited by. So now see, this size is basically called the virtual memory. Virtual memory. Virtual memory size or the software size, both are the same things. So virtual memory size is basically limited by secondary memory. As if secondary memory is less, if it is 10 GB, we can't store 100 GB program now. Thus, it is limited by the available secondary storage. This option is true. But see, we are having 100 GB game. Let us suppose this will come over here. 100 GB will occupy over here, and we have 1024 greater than 100. But when we want to bring it to RAM, RAM is only suppose 32 GB. So we can't bring it to the RAM. So this virtual memory here we are using virtual memory concept. So what we do, we divide this 100 GB file into various pages, and we divide main memory into frames, or we can also do segmentation. This is a paging concept, and we bring only some of the pages into main memory frames. Like if there are 10 GB pages, then we bring, let us suppose, 2 pages in the main memory, 10 GB and 10 GB, 20 GB. Thus, we can easily accommodate this. So, is the size of virtual memory 100 GB limited by the size of main memory? No, it is not limited. We can have any amount of main memory and we can bring the pages to the RAM. So, it's not limited by the main memory. Now, what is this MAR? MAR is basically, let us suppose when CPU generates the address, CPU generates the address according to this process. So, according to the 100 GB process, CPU generates the address. So if, let us suppose, we have 2 to the power 16 bytes, or we can say 64 KB, 64 KB program, then this memory address register will have 64 bytes or 16 bits. It will have 16 bits, so that it can represent 2 to the power 16 bytes of memory. And if this is limited to, let us suppose, 100 bits, then it can only represent 2 to the power 100 bytes. So thus, this size of this memory address register also limits the size of this physical memory. As if we can't basically scan this memory by doing this, let us suppose it's x bytes. Then if 2 to the power x is less than the size of our program, then we can't just basically access the lower parts of the program. Thus, we can easily say that it is limited by the size of the memory address register. This is true. All of the above, no, as option C is false. None of the above, no. So answer is option, both A and B are true, option F. This question belongs to computer organization subject and was asked in GATE 1991, and the topic name is microprocessor, and basically 8085 microprocessor. So the question states, choose the correct alternatives, more than one may be correct, and write the corresponding letters only. The trap interrupts mechanism of the 8085 microprocessor executes the RST by hardware, executes an instruction supplied by the external device through the INTA signal, executes an instruction from the memory location 20H, executes a NOP, and none of the above. So what is basically this trap? So trap is basically an interrupt signal. Trap is basically an interrupt signal in 8085. So whenever a hardware device wants to perform some operation, it sends an interrupt to the CPU. So what are the various types of interrupts in 8085? In 8085 we have trap interrupt, RST 7.5, 6.5, 5.5. We have INTR and we have INTA. It's active low and rest are active high interrupts. So let us see all the options one by one. So option A states executes the RST by hardware. So why is this trap used? First, let me tell you this. So trap is basically used to cut the input voltage. We will have CPU and there will be some input voltage. So trap is used to cut the input voltage to reset the processor in the event of loss of power. Like when power goes, trap is used to basically cut this input voltage. Now let us see option A. Executes the RST by hardware. No, this is not an option, as RST is basically different interrupt. RST is different, here you can see, and trap is different. Option B. Execute an instruction supplied by external device through the INTA signal. No, INTA signal is different and trap is different. Both are different things. So option B is also false. Option C. Executes a signal supplied by the external. Option C. Executes an instruction from memory location 20H. Okay, so all these interrupts have different memory location, but here RST4 has basically the memory location 0020H, hexadecimal location, and not the trap. Trap has a different memory location. So option C is also false. Option D executes a NOP instruction. No, NOP instruction is not at all related with this trap interrupt. So answer is option E, none of the above. This question belongs to computer organization subject and was asked in GATE 1991, and the topic name is microprocessors, specifically 8085 microprocessor. So the question states, choose the correct alternatives, more than one may be correct, and write the corresponding letters only. The ALE line of an 8085 microprocessor is used to latch the output of an input-output instruction into the external latch, deactivate the chip select signal from the memory addresses, latch the 8 bits of the address line AD7 to AD0 into an external latch, find the interrupt enable status of the trap interrupt, and none of the above. So here this is the pin diagram of 8085. Here you can see where is ALE. So ALE is present over here. So you can easily see these signals which have a bar over here are active low, and this is an active high signal. So ALE is an active high signal. Its full form is address latch enable. So why is it low? So it is an active high pin. So when it is supplied with a high pulse, when it is supplied with a high pulse, then this pin will become activated. And when this pin is activated, it demultiplexes the lower address bus. So we have AD0 to AD7, AD7. Let me write it like this. We have AD0 to AD7. Then we have A8 to A15. So when this pin is provided with an active high signal, then it demultiplexes the lower address bus, which is A0 to A7 or AD0 to AD7 from the lower address or data bus. So it demultiplexes this. So the answer is option C. Latch the 8 bits of address line AD0 to AD7 into an external latch. This question belongs to algorithm subject and was asked in GATE 1991, and the topic name is time complexity. So the question states, choose the correct alternatives, more than one may be correct, and write the corresponding letters only. Kruskal's algorithm for finding a minimum spanning tree of a weighted graph with n vertices and m edges has a time complexity of order of n square, order of m into n, order of m plus n, order of m log n, and order of m square. So let me first tell you what is a spanning tree. So suppose we have a graph G, something like this. Let us suppose we have 5 edges, and it is a weighted graph. So let us suppose the weights to be like 10, 20, 30, 40, 50. Yeah. So what is a spanning tree? Spanning tree is basically a subgraph of G, which is a tree. So what is the meaning of tree? It should be acyclic and it should be connected, which is a tree having, if it has m vertices, m edges, and n vertices, which is a tree having n vertices and n minus 1 edges. So what can be a spanning tree? So this one can be a spanning tree, yes, for sure, and this one can be a spanning tree for sure, but both these spanning tree will have different weights. This will have a weight 10 plus 20 plus 40, 70 weight, and this will have a weight 10 plus 30, 40 plus 50, 90 weight. So what is the minimum spanning tree? A spanning tree having a minimum weight is a minimum spanning tree. So in this question, minimum spanning tree is this one. So we need to find what is the minimum spanning tree. For minimum spanning tree, MST, we have Kruskal algo, and we have Prim's algo. So let me tell you in brief about Kruskal algo. So what we do in Kruskal algo is that we select the minimum edges such that there is no cycle formed. So first of all, let me make all the vertices. So what is the minimum weight edge? Is 10. Is there a cycle formed? No. So we will add it. What is minimum weight edge? Next minimum 20. Is there a cycle formed? No. So we will add it. Next minimum 30. Is there a cycle formed? Yes. So we will not add this. So we will not add this 30. 10 is done, 20 is done, 30 is done. Next minimum 40. 40. Is there a cycle formed? No. What are the number of edges we have added? Equals to 4 minus 1, 4 vertices and 3 edges. So it is a MST with weight 40 plus 20 plus 10, which is 70. So this is the Kruskal algo. So we know in Kruskal algo we need to find the cycle. So cycle detection, if it is done by union find algo, if union find algo is used to do the cycle detection, and we are assuming graph is represented as, there are two methods, adjacency matrix and adjacency list. If we are using adjacency list, then the complexity comes out to be order of m log m. Okay, so the complexity here comes out to be order of m log m. Now let me tell you further things. So how can we say this? Now let us suppose it's order of m log m, but here there is no option like this. Now suppose, what is a complete graph? Complete graph is a graph which has, if it has 4 vertices, all the each vertex is connected to every other vertex. So number of edges equals to n into n minus 1 by 2. So we can write m as order of n square. So here we can write m as, or m log n, as if m is order of n square, then m is also order of n. Here m can be order of n also, as number of vertices and edges can be of the same order. So we can have order of m log n. So order of m log n is correct. Now let us further modify this. Can we write log n? Can we write log n as order of n? Yes, definitely we can write log n as order of n. So we can write this as order of m into n. So this is also correct. Now can we write n as order of m? Yes, we can write n as order of m as m equals to n into n minus 1 by 2. So we can write n as order of m. So here we can write this equal to order of m into m, which is equals to order of m square. So option E is also correct. Can we write equal to order of m plus n? No, it's linear complexity, it is not equal. Can we write equal to order of n square? No, this is also false. So answer is B, D and E. This question belongs to algorithm subject and was asked in GATE CSE 1991, and the topic name is stacks. So the question states, choose the correct alternatives, more than one may be correct, and write the corresponding letters only. The following sequence of operations is performed on a stack: push 10, push 20, pop, push 10, push 20, pop, 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 push 20, pop. The sequence of values popped out is 20, 10, 20, 10, 20, 20, 20, 10, 10, 20, 10, 20, 20, 10, 20, 20, 20, 10, 20, 10. So what is a stack? Stack is basically a data structure which follows the LIFO property. So what is LIFO property? Last in, first out, which means the item that is pushed in the last will be popped in the first. So let us start executing it. We have pushed 10, so we will push 10. Okay, then we have pushed 20, so we will push 20 in the stack. Then we have pop, so pop will remove the last in. So last in was 20, so it will remove 20. So 20 will be popped out. And let us make a list of pop list. Pop list has 20. Now we have push 10, so 10 will be pushed. Then we have push 20, 20 will be pushed. Then we have a pop, so 20 will be popped and will come in the pop list. Then we have a pop, means 10 will be popped and will come in the pop list. Then we have pop, means 10 will be popped and will come in the pop list. Then we have push 20, so all these three are popped. Then we have push 20, so 20 will be pushed. Then we have pop, which means 20 will be popped and will come in the pop list. And what we need to tell? We need to tell the sequence of values popped out is. So the answer is 20, 20, 10, 10, 20. 20, 20, 10, 10, 20. So answer is option B. This question belongs to the programming topic and the Pascal programming subject and was asked in GATE 1991. So the question states, choose the correct alternatives, more than one may be correct, and write the corresponding letters only. Consider the following Pascal function. So we have a function by the name x, where m is a parameter and it returns integer. So what it does, here we have defined I to be an integer and we have begin and end statements. Here we have I equals to 0. So we do this while I square is less than m, and we do I equals to I plus 1 and x equals to I. And after this, Again we go to this while loop. So we need to tell the function called xn, if n is positive will return floor of root n, floor of root n plus 1, seal of root n, seal of root n plus 1, or none of the above. So as we have to give this for floor and seal, so let us do one thing. If we want to tell for floor as well as seal, then better take two options. A perfect square like 16. Let us take 2. Let us take 4. Yeah, 4 is a perfect square. Let us take 4, and a non-perfect square like 5. Okay. So how it will evaluate? So first of all, it will let us do it for 4 first. So it will do I. It will come over here and do I equal to 0. Then it will check I square, which is 0 square, is less than m. What is m? M is, here we are providing x of n, which means x of 4. We are running it for x of 4, and when it goes into the function x, this 4 becomes m. So we will see 0 square, which is 0, is less than 4. Yes. So we will do I equals to I plus 1. We will do I to be 1, and then do x equals to I. So x will store I, which means 1. Then we will again go. We will do I square, which is 1 square. 1 is less than 4, yes. So we will do I equals to I plus 1 and store the value of I in x. Then we will again check 2 square, which is 4, is less than 4. No. 4 equals to 4, not less than 4. So we will not evaluate this and come out of the loop. And here we are returning x. So we need to tell here x is being returned. So what x store? X stores 2. So what options can be correct? Root 4 is 2. Its floor is 2. Yeah. Root 4 is 2. Its floor is 2 plus 1, 3. No. So option B is false. Root 4 is 2. 2 seal is 2. Yes, this can be true. Root 4 is 2. 2 seal is 2 plus 1, 3. So this is also false. Now let us do for 5. So we have x of 5. So 5 is stored in the variable m. So we have I equals to 0. And then we have, first we will do 0 square. 0 is less than 5. Yes. So we will do I plus plus. And then we will store this value in x. So x will store I value, which is 1. Then we will do I plus plus. We will check 1 square is less than 5. Yes. So we will increment it to 2 and we will store it in x. Then we will check 2 square is less than 5. Yes. So we will increment it to 3 and store it in x. Then we will check 3 square, 9 is less than 5. No. So we will return x, which is 3. So 5 will return 3. So what is this? Root 5 floor plus 1. What will it evaluate to? It will evaluate to root 5 floor is, no, this was wrong. This was wrong. So we have to check for option A and C. So option A is root 5 floor. So what is root 5 floor? Root 5 is 2 point something. Root 5 is 2 point something, and its floor, it's 2. So this is also false, as it is returning 3, but according to this option it should return true. What is option C? Root 5 seal. So what is root 5? Is 2 point something, and its seal is 3. So answer is option C, as it is verifying for both a perfect square and a non-perfect square. So answer is option C. This question belongs to compiler design subject and was asked in GATE 1991, and the topic name is linker and loader. So the question states, choose the correct alternatives, more than one may be correct, and write the corresponding letters only. A link editor is a program that matches the parameters of macro definition with locations of the parameters of the macro call, matches external names of one program with their location in other programs, matches the parameters of subroutine definition with location of parameters of subroutine call, act as a link between text editor and the user, act as a link between compiler and the user program. So what is a link editor? So another name for link editor is a linker. So I will tell you the phases during the compilation. So the phases during the running of a program. So they go on like this. First of all, we have our high level program, which is written in a.c file. Then we have pre-processing. Then we have compilation done by compiler. Then we have assemblation done by assembler. Then we have linking done by linker. Then we have loading done by loader. And here our program runs in the main memory. Program runs in main memory by CPU. Okay, so we have A.C file. So what pre-processing does? We have certain macro definitions like hash define a value of pi to be 3.141 in our programs, and wherever we have used pi in a program during the lexical analysis phase, it will be replaced by 3.141 during lexical analysis phase of the compilation. So matches, here you can see this option matches externally matches the parameters of macro definition with location of the parameters of the macro call. This is false, as this is done by the lexical analyzer of a program, not by the linker. Now what compilation does? Here we have A.C file. It converts this file into assembly level language file. Converts into assembly level language. It's machine dependent. Then we have assembler. What assembler does? Assembler converts it to 0 and 1s. Now what happens is that suppose we have a program, and here we have certain include statements like hash include some file, hash include mat.h, and then we have used some functions like square root function or some other function, power function. So these functions are not defined in a program. So what we does, we go to this mat.h header file and then to the library file, and then get the code for the square root and power function and place it over there. This is the static linking. So in static linking, place the code over here. So if we place the code, we need to do two things. We do need to do relocation of the code, as certain addresses of might get changed. Here a variable a might have certain different address, and after some code come before it, square root comes before that, a address will change. Thus we need to do the relocation, and what it does, it resolves the external calls or symbols. As square root was an external call, power was an external call, so it resolves the call by placing its code in our given code. So let's see, matches the external names of one program with their location in other programs. Yes, this is what linker does. It's linking part. Then what we have loader. Loader just loads our program. It just finds what's the start address and then loads in the memory from that start address our program. Now let us see option C. Matches the parameters of subroutine definition. So here we have subroutine like a function. Here it has different parameters, and here inside we have used those parameters. So what it is saying? It is saying it matches the parameters of subroutine definition, which means it matches A and B with the location of parameters in subroutine call. With this A and B, no, it's nothing to related with linking. It's false. Act as a link between text editor and user. No, it has no link with this question. Act as a link between compiler and the user program. No, this is false. As linker do not act as a link, this whole pipeline act as a link between the user program as well as the compiler. So this is also false. So answer is option B. This question belongs to compiler design subject and was asked in GATE CSE 1991. And the topic name is parsers. So the question states, choose the correct alternatives. More than one may be correct and write the corresponding letters only. Indicate all the true statements among the following. Recursive descent parser cannot be used for grammar with left recursion. The immediate form for representing expression which is best suited for code optimization is postfix form. A programming language not supporting either recursion or pointer type does not need the support for dynamic memory allocation. Although C does not support call by name parameter passing, the effect can be correctly simulated in C. No feature of Pascal typing violates strong typing in Pascal. So let us see all the options one by one. So what is a recursive descent parser? A recursive descent parser is a top-down parser. Top-down parser. So what it does? It start with the terminal and move to. It start with the non-terminal, and move to the terminals down the tree. But there is an issue. If we have left recursive grammar like this, E implies E plus T or T implies T star F or F, or F implies ID, then before giving this grammar to the recursive descent parser, we must remove the left recursion. If we do not remove left recursion, then what happens here? You can see E and E, this is left recursion, T and T, this is left recursion. If we do not remove this left recursion, then we will get an infinite loop if we want to generate a string or if we want to verify a string. So recursive descent parser cannot be used for grammar with left recursion, yes, as it may fall in infinite loop. Now let us see what option B states. Option B says that the immediate form for representing expressions which are best suited for code optimization is postfix form. So during compilation, we have various steps like lexical analyzer, syntax analyzer, semantic analyzer, intermediate code generation, code optimization, and code generation. But this intermediate code can be of various forms. Like we can have three address code. We can have three address code. We can have directed acyclic graph representation, or we can have postfix representation, and many more. Before this code optimization, it is saying is postfix the best form for code optimization? No, this is not true. As postfix is not the best form, we can have DAG as well as three address code also. They will be equally optimized. So option B is false. Now let us see option C. Option C states that a programming language not supporting either recursion or pointer type does not need the support of dynamic memory allocation. So dynamic memory allocation is done in heap. But if we do not have pointers and if we do not have recursion, then assume the languages like Java, object-oriented language. Here we need to create objects. Yes, we need to create objects. Let us suppose it do not have recursion, it do not have pointers. But still objects are created in heap. So thus, and heap has dynamic memory allocation. Thus for these objects we need heap. And even for dynamic structures like trees can also be present in Java. For trees we need this dynamic memory allocation. For linked list we need dynamic memory allocation. So we basically need the dynamic memory allocation. So option C is also false. Now let us see option D. So option D states that although C does not support call by name parameter passing, the effect can be correctly simulated in C. Let us suppose we have a function fun and it has two parameters a and b. And here in this function we are using somewhere a and somewhere b. Now what happens in call by name is, let us suppose we call this function fun with 3 plus 2 and 4 plus 3. So what we will do, we will just substitute 3 plus 2 over here in entire code, and in place of b we will write 4 plus 3. So this is called as call by name. But C do not have call by name. So how can we simulate this? So we can easily simulate this by using macro substitution. What is macro substitution? You might have seen we have hash define statements. So we will define hash define. We will define a to be 3 plus 2 and hash define b to be 4 plus 3. And during the lexical analysis phase of compilation, what we will do, we will just put 3 plus 2 in all places of A and 4 plus 3 in all places of B. So it can be easily simulated. Thus option D is also true. Now let us see option E. Option E states that, let me first clear these things out. So option E states, no feature of Pascal typing violates strong typing in Pascal. So for this, you can refer to this statement. This has been taken from Stack Overflow. So it states, a statistically typed language has a type system which is checked at compile time by the implementation. So statically, there are two types. We can have static typing or dynamic typing. Dynamic typing means we do not need to refer to the type. Like in Python, we just write a equals to 5. Or we can also have a equals to Vivek, or something like that, a equals to gate. This is dynamic typing, as we are not specifying the type of a during writing the code. Only in the runtime the type would be specified. And in static typing, we need to write the type. We need to do it a equals to 5. So this is static typing. So static type language has a type system which is checked at compile time, but by the implementation. Let me first increase the font a bit. Yeah. Yeah. Now, in strong type language, it is not possible for the programmer to work around the restriction imposed by this type system. So these are strong type language. Now it is asking about Pascal. But Pascal was intended to be strong type, but an oversight in the design unchecked variant record. This is this feature due to which it is a weak type language and it's not a strong type language. So option E is also false. So answer is option A and option D are true only. This question belongs to operating system subject and was asked in 8 CSE 1991. So the question states, choose the correct alternatives, more than one may be correct and write the corresponding letters only. Indicate all the false statements from the statements given below. We need to tell which all are false. So option A, the amount of virtual memory available is limited by availability of secondary memory. Any implementation of a critical section requires the use of indivisible machine instructions such as test and set. The LRU page replacement policy may cause thrashing for some type of programs. The best fit techniques for memory allocation ensures that the memory will never be fragmented. So let us see all the options one by one. So what is a virtual memory? So suppose we have hard disks. Hard disks generally comes in what size? They comes in 1 TB or 1024 GB of hard disk. Now we have certain processes. Processes come in what size? We might have a 100 GB game. We might have a 150 GB software. We might have a 10 GB file. And what are the sizes of RAM that comes? This is secondary memory. This is main memory. Size of RAM is generally 32 GB or 64 GB. Let us assume best case 64 GB. There can be more, but generally we are using this much size RAMs only. And in household computers, we are easily using games of size 100 GBs. So, can we accommodate this entire 100 GB into this 64 GB? No. So, what we do? We divide it into pages. We divide the 100 GB process into pages. Let us suppose of 10 GBs each. And we divide the main memory into frames. And we allocate some of the pages to the main memory frame as per the need. So we can accommodate it. But this entire process need to be in secondary memory, 100 GB. Which means this 1024 should be at least greater than 100 GB. Which means secondary memory size should be at least greater than equal to process size. Or basically all processes size. All processes size. So the amount of virtual memory, which means the size of process available, is limited by availability of secondary memory. Yes, this is true. Now let us see option B. What option B states? So option B says, any implementation of critical section requires the use of indivisible machine instructions such as test and set. Okay. So we have certain approaches for critical section. First are hardware based approach, which require any support from the hardware. And the second one are software based. Now hardware based, even the semaphore is a hardware based solution. Even we have interrupt based solutions. We have TSL, which is test set log based solution. These are all hardware. But we also have purely software solutions like Peterson Algo. It's a purely software based algo. Let me show you the algo. So this is the Peterson algo. How it works? It takes a 10 variable flag and false, and this is the program which process 1 need to execute P0, and this is which the second process need to execute P1. And it makes sure that we have critical section solved for this problem. But this is a purely hardware based solution, not a software based solution. Thus, the option is saying any implementation requires the use of indivisible machine instruction, but Peterson does not require any support from hardware. So this option is false. Now let us see option C. So what option C is saying? Option C is saying the LRU page replacement policy may cause thrashing for some type of programs. So what is LRU? LRU is least recently used algo. And what is thrashing? Thrashing is a condition in which most of the time is spent in resolving the page fault time is very high, which means we are getting very much page faults. Now let us see how LRE works. Suppose we have the request frames as 1, 2, 3, 4, then again 1, 2, 3, 4, then again 1, 2, 3, 4. But main memory has just 3 frames allotted for this process. So what we will do? First we will allot 1, okay, then we will allot 2, then we will allot 3. Now when we come to 4, we see the main memory is full, all the frames have been allotted. So we remove the least recently used. So least recently used, we see which one was the least recently used. So we removed 1 and put over here 4. Then again 1 came. So as again 1 came, so we need to see the least recently used 2. We remove 2 and then put 1 over here. Then 2 came, so we need to remove the least recently used. We remove 3 and put 2 over here. Then again when 3 comes, we remove this and put 3 over here. Thus we are seeing that we are having one page fault every time. Okay, so why this happened? This happened because after 1, 2, 3, when 4 came, so when we removed 1 for 4, then again 1 was referred in the next clock cycle. So if the removed page is referred again in the next iteration, then the LRE page replacement policy will cause thrashing. So option C is also true. Now let us see what option D is saying. So option D says the best fit techniques for memory allocation ensures that memory will never be fragmented. Okay. So what is best fit technique? Let us suppose we have a memory like this. Now we have certain partitions. This is a, let us suppose 10 KB partition. This is 20 KB partition. This is 33 KB partition. And this is 13 KB partition. Now we have certain requests. Let us suppose we have a 10 KB request, we have a 12 KB request, then we have a 30 KB request, then we have a 40 KB request. Let us suppose 35 KB request. Yeah. Okay. So what happens is that, let me do it 40. Yeah. Now it will be perfect. So best fit means we will allot the minimum size available to a given process. So 10 KB. We see the minimum. Minimum is 10. Can it allot completely? Yes. So it's done and dusted. Now 12 KB. The minimum is 14. So we will allot here 12 and this 2 will be wasted. So what is this? This is called internal fragmentation and it can't be used again. Now we have 30 KB. So minimum is 20, not allotted, this 33. So here we will allot 30 KB and 3 will be internally fragmented. Internal fragmentation. Let us suppose it came to be 25. Now we have 25. Now 20 space is not available, but see, here we have 20 KB, here we have wasted 3 KB, here we have 2 KB. So entirely is 25 KB, which is less than equal to our required, but still we are not able to allot. So we have external fragmentation. So is fragmentation problem there? Yes. So the question is saying the best fit techniques for memory allocation ensures that memory will never be fragmented. This is false, as we both have internal fragmentation as well as external fragmentation. So we need to tell which all are false. So the false statements are B and D. So answer is B and D. This question belongs to engineering mathematics subject and the topic name is propositional logic. It was basically asked in GATE 1991. So the question states, choose the correct alternatives, more than one may be correct and write the corresponding letters only. If F1, F2 and F3 are propositional formulae such that F1 and F2 implies F3 and F1 and F2 implies negation of F3 are both tautologies, then which of the following are true? Both F1 and F2 are tautologies. The conjunction of F1 and F2 is not satisfiable. Neither is tautologous, neither is satisfiable, and none of the above. So let me tell you first some of the basic statements. What is a tautology? Tautology is a condition which is always true. Always true. For any value. And what is a contradiction? Contradiction is a value which is always false. And we can also write contradiction to be not satisfiable. Satisfiable. Okay. Now the third one we have contingency. Contingency is a value which can be true or can be false. Which means it is a mixture of true and false. So this is contingency, this is contradiction, and this is a tautology. Now focus on one thing, that here F1, F2 and F3 are propositional formulae. So what is a propositional variable and propositional formulae? Propositional variable. What is a propositional variable? It can have atomic value, which means either true or false. Like when we write P or Q or R, then these are propositional variable. And what is a propositional formula? It is a combination of one or more propositional variable connected by some symbols. Like P is also a propositional variable. Negation of P implies Q, P and Q. All these are propositional formulae. They have atomic values. Propositional variables have atomic values, and their values depend on propositional variable. Okay. Now let us see what this question is saying. So the question says they are propositional variables. Now let me tell you one more thing. What is P implies Q? It is equivalent to negation of P plus Q, or we can write negation of P or Q. Okay. Now it is saying F1 and F2 implies F3 is a tautology, which means F1, we have F1, we have F2, and then we have F1 and F2 implies F3. And then we have another term, F1 and F2 implies negation of F3. They are tautologies. Now we can have various propositional variables, like we can have 3, 4, 5 propositional variables on which this F1 and F2 is defined. So we will have truth table like this. We will have various fields in the truth table depending on these values. If we have n values, then we will have 2 to the power n field in the table. Now they can have various values. The two variables can either be true true, true false, false true, or false false. They can just have these 4 values, and we will have various 2 to the power n values over here. Okay. Now let us see what is the meaning of F1 and F2 implies F3 is a tautology. If we expand this according to this, then we will get negation of F1 and F2 or F3 is a tautology. Tautology means always true for any value. Let us expand it further. So we will get negation. So what is negation of P and Q? It is equivalent to negation of P or negation of Q. So it means negation of F1 or negation of F2 or F3 is always true. Okay. Now let me expand this term. The second one. If this is tautology, then it means negation of F1 and F2 or negation of F3 is a tautology. And if we expand this, then we get negation of F1 or negation of F2 or negation of F3 is a tautology. Now focus. Here we have two terms. This term is common in both. Okay. And here we have or of negation or F3 or negation of F3. So suppose we have terms like, if we can say P or Q is true and P or negation of Q is true, then what it means? It means that whatever with the value of Q can have any value. As here, if Q is true, then here it will be false, and if Q is false, then here it will be true. Which means what Q will have both values, but for both of them to be true, P should always be true. Which means P should always be true. Okay. So here what this means that f1, which means the first term, negation of f1 or negation of f2 should always be true. Always true. It should always be true. Now let us see what are the values of. Now let us draw the truth table for this negation of f1 or negation of f2. Okay, so I will draw the truth table over here. Okay, we have f1, we have f2, then we have negation of f1 or negation of f2. Okay, we can have values like true true, true false, false true, or false false. So what is negation of true? It's false. False or false? It's false. Negation of true is false. Negation of false is true. So it's true. It's true and it's true. Which, and here we arrive to the conclusion that this should always be true, which means this condition shouldn't occur. This condition shouldn't occur, and all these are acceptable situations. So let us see the options now. Both f1 and f2 are tautologies. No. If both are tautology, then we will get false and this condition shouldn't occur. So A is false. The conjunction f1 and f2 is non-satisfiable. Now let us find the value of f1 and f2 for these three conditions. It's false, and it's false. It's false means it is contradiction, and contradiction is also called non-satisfiable, which means option B is true. Neither is tautologous. No, it's false. As we can have f1 or f2 can be tautologous if the other one is false. Option C is false. Neither is satisfiable. Tautology means satisfiable. No, this is also false, as we can have satisfiability can be there. This is false. Option E is false. So answer is option B. So let me brief it up. What we have done, we have found out that both are tautologies, so we have expanded them. When we expanded that, then we came to know that f1 do not depend, as here it will be true, here it will be false. Thus the first part should always be true. For first part to be true, both of them can't be true, so both of them can't be tautology, and we found out that f1 and f2 is a non-satisfiable or it is a contradiction. So answer is option B. This question belongs to theory of computation subject and was asked in NIELIT 1991, and the topic name is regular expressions. So the question states, choose the correct alternatives, more than one may be correct, and write the corresponding letters only. Let r equals to 1, 1 plus 0 whole star, s equals to 1, 1 star 0, and t equals to 1 star 0 be three regular expressions. Which of the following is true? Ls is a subset of Lr and Ls is a subset of Lt. Lr is a subset of Ls and Ls is a subset of Lt. Ls is a subset of Lt and Ls is a subset of Lr. Lt is a subset of Ls and Ls is a subset of Lr. None of the above and both A and C. Now let us write these expressions first and the language corresponding to them. If we have 1, 1 plus 0 whole star. So what is the meaning of 1 plus 0 whole clean closure? Which means we can have any number of 1s and 0s followed by 1. Which means we can have none followed by 1. We can have 1 0, we can have 1 1, we can have 1 1 0, we can have 1 1 1, we can have anything 1 0 1 1, 1 1 0 1 0, we can have anything. Now let us see what is S. It is 1 1 star 0. Which means it will have 1 0 and in between it can have any number of ones, which means it has 0 ones, 1 1 in between, 2 ones in between, it can have 3 ones in between, and so on. Now let us see T. T is 1 star 0, which means any number of ones followed by 0. So 0 ones followed by 0, 1 1 followed by 0, 2 ones followed by 0, 3 ones followed by 0, 4 ones followed by 0. Now let us see what are the options. Ls is a subset of Lt. Okay, now we have Ls is a subset of Lr. We have Lr is a subset of Ls. Lr is a subset of Ls. Then we have Ls is a subset of Lt is done. Then we have Lt is a subset of Ls. And yeah, all these four options are four things are present in these options. Now let us evaluate them. Ls is a subset of Lt, which means everything in Ls is in Lt. 1 0, yes it is there. 1 1 0, yes. 1 1 1 0, yes. As this is starting with 1 and ending with 0, and this is starting with 1, so definitely this will be true. LS is a subset of LR. LS is a subset of LR we have seen. Now let us see LS is a subset of LT. Yes. So LS is a subset of LT. 1 0. Is it there? Yes. 1 1 0. Yes. 1 yes. 4 1 0. Yes. So why is it true? It is starting with 1, ending with 0. It is ending with 0. So 0 is fine. Now we have a 1. Yes. A 1 is fine. And it has any number of 1s followed by this. So this will be true only. So this is true and this is true. Let us see LR is a subset of LS. LR is a subset of LS. See, we have 1 in LR, but LS do not have 1, as it should have both 1 and zeros. So this is false. LT is a subset of LS. LT is a subset of LS. Here we have 0, but here we can't have 0, as it should definitely have a 1. This is false. Let us see the options. LS is a subset of LR. It's true. LS is a subset of LT. Is true. LR is a subset of LS. It's false. LS is a subset of LT. It's true. But LS is a subset of LR. It's also true. Okay. LT is a subset of LS. It's false. None of the above, no. So answer is both A and C. Option F, both A and C are true. This question belongs to theory of computational subject and was asked in GATE 1991. So the question states, choose the correct alternatives, more than one may be correct, and write the corresponding letters only. Which of the following is the strongest correct statement about a finite language over some finite alphabet sigma? It could be undecidable, it is Turing machine recognizable, it is context sensitive language, it is regular language, and none of the above. So what is a finite language? A finite language, let us suppose LF, is a language which has finite number of strings. It can have 10 strings, 100 strings, 1000 strings, but it is finite. Let us suppose it accepts 0, 1 0, 0 0 1, 1 1 0, 1 0 1 0, and 100 strings like this. So can we generate a finite automata? Yes, we can generate a finite automata. Like we will have 1, 0 and a final state. Then we can have 0 0 1. So we can easily make for finite state 0 0 1 we will have like this. Then we will have 1. Then we will have a 1 over here. Then we will have a 0 over here. So for each string we can just generate the states. So we can generate a finite automata for finite language. Thus, it is regular. Anything for which we can generate a finite automata is a regular language. Now, we know. Now, let me tell you a diagram. So, it is regular for sure. And this is the most strongest statement. But as it can have more than one correct answers. So, we have to see other options too. So, this is regular language. This is CFL language, context free language. This is CSL language, context sensitive language. This is REC language, recursive language. This is RE language, recursively enumerable language, and all these are non-recursively enumerable languages. So let us see. It could be undecidable. So undecidability comes under non-RE. No, it's as it is regular, so it is decidable. Option A is false. Now let us see option B. It is Turing machine recognizable. So all RE languages are Turing machine recognizable, or even REC are Turing machine recognizable. And as regular is a subset of RE, so we can easily recognize it by Turing machine. So option B is true. It is context sensitive, yes. Any lower language is also upper language. So regular is also CFL, it is also CSL, it is also REC, and it is also RE. But a middle language like CSL is REC and RE. Okay, so it is a context sensitive language, but CSL may not be a CFL, and CSL may not be regular. And D was also true, and none of the above is false. So answer is option B, C and D are true, but the strongest one is it is regular. But we can have it is also CSL and it is also Turing machine recognizable. So B, C, D are correct options. This question belongs to programming subject and was asked in GATE CSE 1991. So the question states, Give short answers to the following questions. Convert the following Pascal statement to a single assignment statement. If x is greater than 5, then y equals to true, else y equals to false. Let us see the answer for this. So we have an operator called an ternary operator. First, let us see what this program is doing. If x is greater than 5, then it assigns y the value true, else if x is less than equal to 5, then it assigns y to false. So we have ternary operator which is given by this. So here its basic syntax is a condition followed by the operator, and then it has C1 and then colon C2. C2 means the statement which is executed when condition is true, and this is executed when condition is false. So how can we rewrite the given statement? We can rewrite this as x is greater than 5. We are asking this, and if it is true, then we are assigning y to true, else we are assigning y to false. So let me write this over here. It is equivalent to x is greater than 5, then y equals to true, else y equals to false. Now let us see second question. So in the first one we have just used the ternary operator of Pascal. Now the second option says convert the Pascal statement. This is the statement. What is the statement? It is repeat S until B into an equivalent Pascal statement that uses the while construct. So we have to rewrite this using the while loop. So what's the syntax of while loop? The syntax of while loop is something like this. While a condition, and while that condition is true, it will execute some statements. Let us see S1. So it will keep on executing S1 till that condition is true. So we can rewrite this as while B we will do S. While B we will do S. So this one is equivalent to while B we will do S. This parentheses are optional if there is a single statement. We can write this without the parentheses also. Now let us see the question 3. So part 3 says obtain the optimal binary search tree with equal probabilities for the identifier set A1, A2, A3 with if, stop and while. So let me tell you what is a binary search tree. In binary search tree, we have a node and all the values which are less than, if this is x, then it will have all the values less than x, and it will have all the values greater than x. Now suppose we have a tree like this. This has A, this has B, this has C, and this has T. Okay. Now, what is an optimal binary search tree? Let us suppose A occurs with a frequency f1, B with a frequency f2, C with a frequency f3, and D with a frequency f4. So, then what is the cost of searching A, B, C, and D? So, it is equals to A into f1. A is the cost and f is the frequency, plus bf2 plus cf3 plus df4. In binary search tree, optimal binary search tree, we try to minimize this frequency by creating a tree such that this value is minimized. Here we will have A. So the values that will come over here are, in case of A, B, C, and D, we will have the number of times it was searched. A can be searched in one comparison, so we will have 1 into f1. B can be searched in 2 comparisons, so we will have 2 into f2. C can be searched in 2 comparisons for this and this, so it will have 2 into f3, and D can be searched in 3 comparisons. First with this, then with this, then with this. So we have 3 comparisons. So we need to minimize this value. Minimize the value. Now let us see. Here we are given that we have 3 symbols A1, A2 and A3 such that all have equal probabilities. Let us suppose 1 by 3, 1 by 3 and 1 by 3. So A has frequency 1 by 3. Frequency or probability, we can say all 3 are same. which means it do not matter which node comes at what place. So we can have various representation. Either it can be like this, A, B and C can be anywhere as all has equal probabilities. Or we can have it like this, A, B, C. Or we can have it like this, A, B and C. We can have various structures, like we can also have something like A, B and C and various. But all these will have equal cost. The cost will be equal to A1 with a frequency 1 by 3, A with a frequency 1 by 3, B with a frequency 1 by 3, plus C with a frequency 1 by 3. So this is the cost. And for this, the cost will come out to be A with a frequency 1 by 3. But here, what is the number of comparisons for A? A will have 1 comparison, B will have 2 comparisons, C will have 3 comparisons. So it is equals to 6 by 3, which is equals to 2. Now let us see this one. A having 1 comparison with a frequency 1 by 3, B having 2 comparisons with a frequency 1 by 3, C having 2 comparisons with a frequency 1 by 3. So it is equals to 5 by 3, 1 point something. Let us suppose 5 by 3 and this is 6 by 3. So this is the optimal binary search tree. Optimal means it will have minimum frequency. So the answer to this question will be, the tree will look something like this. A1 over here, A2 over here and A3 over here. We can have A1, A2, A3 over any places, but the structure will be like this only. This question belongs to the subject Digital Logic Design and was asked in GATE 1991. So it has 3 parts. Let us see all the parts one by one. So part A is, analyze the circuit in the figure given below and complete the following table. So here we have been given a figure which is a circuit and we need to complete this table. So here what we will do, we will find the value of this Qn. So Qn. So this basically are AND gates and this is an OR gate. This is an OR gate and this is an AND gate. So what is the input for the first AND gate? So it's basically OR of 3 terms. The first term is an AND gate. What is its inputs? Its input is the previous input Qn minus 1 AND with the A plus this one which is A into B plus this one which is B into the previous input, B into Qn minus 1. Now we need to fill this table. So when A and B are 0, what is the value of Qn? When A and B are 0, this becomes 0, this becomes 0 and this becomes 0. So the whole terms become 0. Okay. Now the next thing is, when A is 0 and B is 1. When A is 0, this becomes 0, this becomes 0 and B is 1. So this becomes 1. So we get Qn equals to Qn minus 1. Qn minus 1. Now when A is 1 and B is 0. If B is 0, this terms become 0 and this term becomes 0. And A is 1, which means this term become 1. So Qn equals to Qn minus 1. When both are 1, then we have this term as well as this term as well as this term. So A is 1, so 1 into something is that only, Qn plus 1 plus 1 into 1 is 1 plus 1 into anything is that term only. Qn equals to 1 plus anything. 1 plus anything is always 1. So 1 plus anything is always 1. So we get answer to be 1. The answer is 0, 1, Qn minus 1 and Qn minus 1. Now let us see option B. So option B states, find the, let me first clear this out. Option B states that find the minimum sum of products form of the logic function f abcd equals to sigma m 0 to 8 10 15 plus sigma d 3 10 3 11 12 14, where m and d represent the minterm, m is the midterm and d is the don't care terms. So first of all, here there are 4 variables. So let me draw the 4 variable K-map for you guys. So 4 variable K-map looks something like this. It's for minterms. Okay. Here we have AB. Here we have CD. It's 0 0 0 1 1 1 1 0. it's 0 0 0 1 1 1 1 0. And let me write the indices over here. 0 0 0 0, it's 0. 0 0 0 1, it's 1. 0 0 1 1, it's 3. 0 0 1 0, it's 2. This is 4 5 6 7. This is 8 9 10 11 12 13 40 as well as 50. Now let me fill this. Here we have min terms in 0 2 8 10 15. So 0 2 8 10 15. And we have don't care terms in 3 11 12 14. So 3 11, then we have in 12, and then we have 1 in 14. Okay, so now let us do the grouping. So how can the grouping be done? Here we can have these four can be grouped into one. Okay, yeah. And how can be the second grouping? For the second grouping, we can group either these two together, but then this won't come. Okay, for the second grouping, we can group this one together. So what will be the output? So the output for this four corner groupings would be this and this, which means this is 0 and this is 1, which means C will get cancelled and we will get D complement. Okay, for this and this, the different things, which is A will get cancelled, we will get B complement. Okay, for this term, let us see. This is 1, this is 1, this will remain, 1 0 will get cancelled, so we will get C. And for this term, this will get cancelled and we will get AC. So it is AC plus B complement D complement is the expression. Now let us see question 3. So question 3 is, it is given that find the maximum clock frequency at which the counter in the figure below can be operated, assuming that the propagation delay through each flip-flop and each AND gate is 10 nanosecond. Okay, so we have a delay of 10 here, we have a delay of 10, a delay of 10 here, a delay of 10 here, a delay of 10 here, and a delay of 10 here. Assume that the setup time for the inputs of JK flip-flop is negligible. Okay, so how is the table for JK flip-flop? So the table for JK flip-flop goes something like this: 0 0 0 1 1 0 1 1. What is the expression? Here we have Qn plus 1 is equal to J Qn complement plus K complement Qn. So for 0 0, here we have J as 0, so this will get cancelled. K complement, 0 complement is 1, so we will get here Qn. This term will get 0 as J0, this term will have 1 complement 0, so both will get 0. 1 into Qn complement and 0 into, so we will have 1 into Qn complement plus 0 complement is 1 into Qn, so we will have Qn plus Qn complement, which is 1. Then for the fourth term, we will have 1 and 1, so 1 complement 0 will get cancelled, we will get 1 into Qn complement. So here we can easily see that in the JK flip-flop, the output toggles when both J and K inputs are 1. So what we must do, we must ensure that for each clock, the output from the previous stage reaches the current state. Let me tell you what is this setup time. So what is setup time? Setup time is given here negligible, but it means that as soon as the data is stable, the next clock can be given. As what is the definition of setup time? Setup time is the minimum time before clock active edge, that data must be stable for it to be latched properly. And as this is negligible, which means as soon as the data is stable, the next clock can be given. Now let me tell you what should be the answer for this question. So here we know what is the propagation delay. What is the propagation delay? The propagation delay, as this is given that the propagation delay for each flip-flop is 10 nanosecond. Okay, so we get the time for the output from flip-flop once the clock is given is propagation delay is TPD. Okay, now let me rename this as flip-flop 1, this as flip-flop 2, and this as flip-flop 3. Now time for input to reach flip-flop 0. Okay, now time to reach the input to flip-flop 1. So what is the time in which input will reach over here? Here you can see there is no gate, so the time is 0 nanosecond. Time for flip-flop 1 is 0 nanosecond. What is the time for the input to reach flip-flop 2? It has to go through this AND gate. So the time is delay of this. It is 10 nanosecond due to one AND gate. Time for the input to reach flip-flop 3, it has to go through these two AND gates. So it is equals to 10 plus 10, which is 20 nanoseconds. So here, what is the minimum time? What is the minimum time for clock? It is equals to 10 nanosecond for this propagation delay plus max of all the gate delays, max of 0, 10 and 20. So time for clock is 10 plus 20, which is 30 nanoseconds. So frequency equals to 1 upon time. It is equals to 1 by 30 nanosecond, which is equals to 33.33 megahertz. So this is the frequency. So the answer is 33.33 megahertz. Here the answer is B complement D complement plus AC, and here the answer is 0, Qn minus 1, Qn minus 1 and 1. This question belongs to digital logic design subject and was asked in 1991. So the question states, using D flip-flop gates, design a parallel in serial out, which means PSO shift register that shifts data from left to right with the following input lines. It is a clock CLK, 3 parallel data inputs A, B and C, a serial input S, and a control input load / shift bar. So let me tell you the diagram for this. So refer to this diagram. This is the diagram for our shift register. So here we have 3 input datas A, B and C. Here this is load / shift complement, where load is active high and this is shift is active low as given in the question. Now here we have AND gates, and here this is an OR gate, and here we have the inputs. Okay, so let me tell you, it works in 2 modes. First is load mode and the second one is shift mode. So when is the load mode activated? Load mode is activated when we are giving an input 1. Okay, so when we are giving an input 1 over here, this gate should come over here, sorry, yeah. So when we give 1 over here, then what happens? Then 1 will come over to this place and 1 will come over to this place, and 1 complement is 0, so 0 will come over to here and 0 will come over to here. Now here Q1 will come and here Q2 will come. So what happens? Q1 and 0, it's 0, and here we have B and 1, which is B. B or anything is B. So B gets stored in this flip-flop, and A comes directly and gets stored in this flip-flop. Now what happens? Q2 and 0 is 0, C and 1 is C, 0 or C is C, so C comes over here and C gets stored over here. So load mode is finished. So what happens in load mode? We have stored A, B as well as C. Now let us see what happens in shift mode. Okay, now we have shift mode. So what we are doing in shift mode? We are providing its active low, which means we need to provide 0 over here and 0 complement is 1. So 1 comes over here. So 0 goes over here, 1 comes over here, 0 goes over here, 1 over here, and here we have what we have? We have Q1, here we have Q2. So Q1 and 1, what is its value? Its value is Q1. Okay, and this is B. B and 0 is 0 only. So 0 or Q1, it's Q1. And here we have Q2 and 1, its value is Q2. 0 or C, its value is 0. Q2 or 0, its answer is Q2. So what happens? So in the flip-flops, flip-flop 1, flip-flop 2 and flip-flop 3. Initially, let us suppose A was, let us take any random bits, 1, 0, 1. So initially we have stored A, B and C, which means 1, 0 and 1. Now as it is G flip flop, so Qn plus 1 is equals to the input, which is G, which means in the next iteration here B is having the value Q1, and what is Q1? Q1 equals to the input of this, which means A, so 1. This is A over here, initially this, which means 1 gets shifted over here. Now what is this value? Third flip flop holding. Third flip flop is holding the value Q2, and what is Q2? Q2 equals to the input according to D flip flop, which means B, which means 0. So we get this in the next iteration. Now in the next iteration, this one will get shifted over here. Thus, it is acting as we are providing parallel inputs and we have serial output. Such that shift is active low and load is active high, and we are having 3 inputs and a clock CLK. So this is the answer for this. Now let me tell you the second question. Let me just minimize it and put it over here for your reference. Okay. So what is the second question? Second question says design a 1024-bit serial in serial out, which is means CISO undirectional shift register using a 1K cross 1-bit RAM with a data input D in, output D out, and a control input read cross write bar. You may assume the availability of standard SSI and MSI components such as gates, register, and counter. So here you can refer to this statement. See. So we are essentially stuffing a 1024 1 cross 1024 FIFO, which is FIFO registers, assuming we want the data back in the same way as we put it. In general terms, receive a bit in memory at address 0. At address 0 we receive it and receive the next bit at address 1, then so on up to address 1024. Our received bit counter is our address generator. Afterward, we can count back using the same counter, thus generating addresses for the RAID. Thus, this is the answer for part A, and this is the explanation for part B. This question belongs to programming subject and was asked in GATE 1991. So the question states, consider the following pseudocode. All data items are of type integer. Here we have procedure P with A, B and C as parameters, and we are doing some work, and then we have procedure Q. So, and it states determine its output if the parameters are passed to the procedure first by value, second by reference, and third by name. Let us see all of them one by one. So first we will see pass by value. So what happens in pass by value? So in pass by value, we are just passing the values to these parameters. So let me show you how it works. So we have x equals to 1, y equals to 5, z equals to 100. Then we call this p with a value x, which means a 1 is passed. X into y is 1 into 5, which means 5 is passed. And z means 100 is passed. And in this function, this value is taken up by a, this is taken up by b, this is taken up by c. Then it has a local variables a and c. So what it does a equals to 2. So a had initially 1. So a had initially 1 from this, c had 100, and b had 5. So it does a equals to 2. So these local variables a is changed to 2. Then c equals to a plus b, which means c equals to 2 plus 5, 7. But these variables x, y and z, which the main function was having, are not changed. We have just passed these values. These values are taken up by these a, b and c's, and these a, b and c's have changed, not these. Thus when we print x equals to and z equals to, then the value printed is x equals to the value of x over here 1 and z equals to 100. Now let us see the second case. Now we have pass by reference. So in pass by reference, the memory location is passed. So let us suppose we have x, we have y, and we have Z. And the memory location is 1000, this is 2000, this is 3000. And it has value 1, it has 5, and it has value 100. Now when P is called, so we call the P with a value X. X means the address 1000 is passed. X into Y. So we perform X into Y in another variable temp, and its address is 4000, and X into Y is 5, 1 into 5 is 5, and we pass 4000 over here. Then we have Z. So Z has address 3000. Now this address will be taken up by A, this will be taken up by B, this will be taken up by C. When we do A equals to 2, so A has address 1000. So at address 1000, it changes the value to 2. Then when we do C equals to A plus B, so it takes the value from A, so A has address 1000, so 1000, the value is 1000 is 2, and B has address 4000, the value at address 4000 is 5, it computes it to be 7 and store it at C. C has address 3000, so at address 3000 it stores 2 plus 5, which is 7. Now this procedure ends, and when we write X and Z, then the values which are written are passed by reference. So X value is 2 and Z value is 7. Now let us see the third case. Third case is passed by name. Let me clear this stuff out. So what happens in pass by name? So in pass by name, when we are passing over here X into Y and Z, then after coming over here, in place of A, we will be writing X in entire code. In place of A, we will be writing X. In place of B, we will be writing X into Y. X into Y. And in place of C, we will be writing Z. So this code becomes X equals to 2, Z equals to X plus X into Y. And these variables are these variables of this main function only. So we have X equals to 1, Y equals to 5, and Z equals to 100. So what happens now? When we do X equals to 2, so this value is changed to 2. Now when we do Z equals to X, so the value X is 2, 2 plus 2 into 5, 10, 2 plus 10 is 12, so we do Z equals to 12. So the answer is, and then when we print X and Z value, then X is 2 and Z is 12. So these are the three answers. This is for option 1, this is for option 2, this is for option 3. Now let us see the second question. So the second part of this question states, for the following code, indicate the output if static scope rules and dynamic scope rules are used. Okay. So let us see first for static scope rules. Static scoping. So what happens in static scoping? In static scoping, if a variable is not present, then we see in the structure, like in the outer structure, what are those variables we will use it. Like for over these A and B, we will use the global ones. For this P, if it is not there, we will use the global one. For this Q, it is there, so we will not use the global ones, we will use the local ones. So let us see how it will work. First of all, when this is main function, this is Q function, this is P function, and these are global variables A and B. So we have global variables A and B. Now when this main is executed, then it does A equals to 1, B equals to 2. A and B are not present in this main, so it uses the global ones. So do A equals to 1, B equals to 2, this is the global ones. Now it calls Q. So when we come to Q, then we have defined these variables inside Q, a variable and a B variable. Then we call P. When we call P, then we have done A equals to 5, B equals to 10. But in P, A and B are not present. We do not have A and B. So what we do? We just check the outer scope. So outer scope is global scope for this. So it do in global ones, it do A equals to 5 and B equals to 10. And then it will call, it will end P and come to Q. Then it will end Q and come over here. Then it will write the value of A and B. As A and B are not present in main, it will check the global ones. So global A and B are 5 and 10. So it will print A equals to 5 and b equals to 10. Now let us see what happens in the second case in dynamic scoping. So in dynamic scoping, what happens is that if we are having scope problem, which means some of the variables are not present in the current function, then we will check the order in which they were called in the stack. I will show you how it will work. So initially, and if main scope problem occurs, then we will check the global ones. So first of all, when we will come over here, we will push main in the stack, and we have some global variables. We have these global variables A and B having some default value or garbage value. Then when we call this main, we push main into the stack. We do A equals to 1, B equals to 2. So as scope problem arises, A and B are not present in the main, so we will check is lower in the stack. As nothing is there below main, so we will check the global ones. We will do A equals to 1 and B equals to 2. Then we will call Q and push Q in the stack. Now what happens? Q has its own variables A and B having some default values. Now you have called P. So when we come in P, we push P into the stack. We see it does A equals to 5 and B equals to 10 assignment. But P do not have A's and B's, so it's checked lower in the stack, Q. So Q has A and B, so it can change its value to 5 and 12. Q values are changed, not P values. Now P ends, so P is popped out. Now we come to Q, Q ends, so Q is popped out. Now we come to main and we write A and B value. So main do not have A and B and nothing is below main, so we check the global ones. So we do A equals to 1, these are global ones, and B equals to 2. So this is the answer for static scoping, this is the answer for dynamic scoping, and these are the answer for call by value, call by reference, and call by name. This question belongs to compiler design subject and was asked in GATE 1991. So the question states, consider the following grammar for arithmetic expression using binary operators minus and divide which are not associative. E implies E minus T slash T, T implies T divided by F slash F, F implies E slash ID, where E is the start symbol. And it has two parts. Let us see each part one by one. Part A states, is the grammar unambiguous? If so, what is relative precedence between minus and divide? If not, given unambiguous grammar that gives divide precedence over minus. First, let me tell you what is the meaning of this non-associative. Non-associative, if minus is non-associative, it means A minus B minus C is not equal to A minus B minus C. And divide is not associative, which means A divided by B divided C is not equal to A divided B whole divided C. Which means we can't change the associativity of this parenthesis. Now, when can we say a grammar is ambiguous? A grammar can be said to ambiguous if any derivation of a string has more than one either parse tree, more than one parse tree, or more than one leftmost derivation tree, leftmost derivation, or more than one rightmost derivation. In leftmost derivation, we are always expanding the leftmost non-terminal, and here we are always expanding the rightmost non-terminal. So the grammar is ambiguous, but finding an ambiguity of a grammar is an NP-hard problem. So how can we prove that a grammar is ambiguous? So we basically try to find out a string for which we can generate more than one parse tree, LMD or RMD. And if we are able to find a string, we directly say the grammar is ambiguous. And if by hit and trial methods we are not able to find any string, then we can conclude that the grammar is unambiguous. Let me try to generate more than one parse tree if I can. Let us take strings like id minus id divides id. Let us try to generate the parse tree for this. So we have E implies E minus T. Okay. Then we have T implies T divides F. Then we have T implies F, F implies ID, F implies ID. So this part is done. No, Here we are generating a wrong thing. So let me try to redo it. Sorry. So here what we will do, first we will try to bring this divide symbol. So what we will do, we will start with E implies T, T implies T divides F. So here we have brought this divide symbol. Now we will do F implies ID. So this part is done. Now what we will do, we will do T implies F, F implies parenthesis, open closed as well as E. Then we will do E implies E minus T. Then we will do E implies T, T implies F, and F implies ID, and then we will T implies F and F implies ID. So we have done it. ID, so we have generated ID minus ID divides ID. But we are only able to generate one string, one parse tree for it. You can try to do some try runs. You will get to know that for each string you can generate only one parse tree is possible. Thus the grammar is unambiguous. So you need to do it by hit and trial method, whether you are able to find a grammar or not. So in this case, we come to the conclusion that the grammar is unambiguous. Now, what's the further part of the question? It says, is the grammar unambiguous? Yes. If so, what is the relative precedence between minus and divide? If not, give unambiguous grammar. So this part has no significance as it is already unambiguous. Now we need to give the relative precedence between minus and divide. Okay. So higher precedence has more depth. What is the meaning of higher precedence? Higher precedence means it should be evaluated first, and we can evaluate an expression first if it has more depth. See, draw the tree for this grammar. E implies E minus T. Then we have T implies T divide F. Here you can see, here divide has more precedence than minus. Thus, divide has more precedence than minus. So the answer is divide has more precedence than minus. Now let us see the second part of the question. So part B states, does the grammar allow expression with redundant parenthesis as ID divides ID? This is redundant, as even if this parenthesis was not there, ID divides by ID will have the same output. And even if this parenthesis is not there, ID minus ID divided by ID will have same output, as we have already seen that divide has more precedence. So divide will be evaluated first and then minus. So we have to see whether this allows these expressions or not. Let us see whether it allows ID divides ID or not. So what we will do, we will try to generate the tree. So we will do E implies T, T implies F, F implies open parenthesis, E and closed parenthesis. Then we will do E implies T, T implies T divide F. Then we will do T implies F, F implies ID. Sorry. And here we will do F implies ID. So here we have generated ID divides ID with an open and closed parenthesis. We have easily generated. So this can generate this. Now let us see whether it can generate the second one, ID minus ID divides ID. So for this, let me try to draw the parse tree. So the parse tree for this will be something like this. E implies, we will have E minus T. Then we can do E implies T, T implies F. We can do F implies ID. For this T, we can do T implies F, F implies open and closed parenthesis E. Then we can do E implies T, T implies T divide F. Then T implies F, F implies ID, F implies ID. Now let us see whether we have generated it or not. We have ID minus open parenthesis, ID divides ID closed parenthesis. Yes, we have generated this. So this means yes, we can generate redundant parenthesis, as this parenthesis is redundant. Why is it redundant? Because even if we have ID minus ID divides by ID, even then as divide has more precedence, so it will be evaluated first only. So there is basically inherent parenthesis is available due to this higher precedence of divide. So there is no need of writing these parentheses. So now what we need to do? Yes, it allows this. If so, convert the grammar into one which does not generate an expression with redundant parentheses. Okay, and we have to do this in minimum number of changes to the given production rules and adding at most one more production rule. Okay, so we are given this grammar. So now what they are asking us is that we should convert this to a grammar which does not generate the redundant parentheses. And for this we can add at most one extra production rule. So how can we do this? Let us suppose we will take it same like this, e implies e minus t. With e dash we will also try to generate e minus t, but not t. T can't be generated with this. Now we will have t implies t dash divides f and id, the same over here. And then t dash can also derive t dash divides f. These are pipelines operator. This is pipeline. T divide f and f, and then we can have f implies e dash pipeline operator id. Now let us try to generate the strings, whether we can have redundant parentheses or not. So id divides id is a redundant parenthesis. Let us try to generate it with this. So how will we do? We will start with e, okay. Then we have to bring this parenthesis. So we will go to e to t, then t to, we can't generate if we come from e to t, and then t to, we can't generate parentheses over here because parentheses can be generated only by e dash. So thus we can't generate this. Thus this is our answer, and this grammar is not able to generate the redundant parentheses. So this is the answer for part B, and we can generate redundant parentheses. This question belongs to operating system subject and was asked in GATE CSE 1991. So the question states, consider the following scheme for implementing a critical section in a situation with three processes PI, PJ and PK. Here we are given the code for the process PI. The code for process PJ and process PK would also be there. It would be same as this one only, but here in place of I we would be using J, in place of J we would be using K, and in place of K we would be using I in this code. And if we can also rewrite the same for process PK, but here in place of I we would be using K, in place of J we would be using, in place of I we would be using K, in place of J we would be using K, and in place of K we would be using, or we can do it like this, like in place of I we can just use K on J, and K in that code would remain the same. K can be replaced with I. Let me rewrite this. See, here if we are rewriting PI for PK, then in place of I we have to write K. Okay. J can be remained as it is, as J has no relation, and in place of K we can rewrite it as I. And if we are rewriting I as J, then in place of I, what we can do is that we can, in place of I we can write J, K will remain as it is, and in place of J we can write I. Okay. Now let me explain you what this question is asking. So it states, does the scheme ensure mutual exclusion in the critical section? Explain briefly. And second part states, is there a situation in which a waiting process can never enter a critical section? If so, explain and suggest modifications to the code to solve the problem. Okay, so here there are three processes, PI, PJ and PK. I have told you the modification that needs to be done in all these three codes. So here we can assume that this turn variable, we have this turn variable, we can assume a global turn variable which is shared among all these three processes, which means changes done in the turn can be seen by any of the three processes. Okay. Now let us analyze the code for PI. Okay, so what it is doing? It is doing flag I equals to true. Then observe this condition. It has while flag j or flag k do. So what it means? It means if either flag j is true or flag k is true, means flag means they want to go in critical section. If either j wants to go in critical section or k wants to go in critical section, then this process can't get into the critical section. Okay, so it ensures mutual exclusion. Mutual exclusion is ensured. How? If flag J is true or flag K is true, no process can enter critical section until the flag of other process is false. Both of them should be false, only then we can enter the critical section, else we can't enter the critical section. Thus, mutual exclusion is ensured. Yes, mutual exclusion is ensured in the code. Now, let us see the second part of the code. So what the second part is saying, is there a situation in which a waiting process can never enter a critical section? Okay, let us see how we can assume this. Okay, so let me remove all these codes. Okay, now assume we are over here and we have turn equals to k. We have a global turn variable which has a value k. Assume this. Okay, now assume that pj wants to enter the critical section. So flag of j equals to true. So what pj checks? Pj comes over here, does flag of j equals to true. Okay, this is done for the j code. Then it checks in place of j, it will check for I. So it will check if flag of I or flag of k is true. Okay, it will check if flag of I or flag of k is true. It will check flag of I or flag of k is true, then it will not enter the critical section. But here you can see flag of I is false and flag of k is false. Only flag of j is true. Thus, what will happen is that pj is executing the critical section. So pj will come to the critical section and it is executing the critical section. Now assume that at this point of time, what happens is that pi arrives. Okay, so now while pj is executing in its critical section, pi arrives. So pi arrives in the code. Initially pj was there, when it entered the critical section, at the same time pi arrived. So when pi arrived, then what will happen is that it will check if flag j or flag k is true. Now you can see that flag j is true, so it can't enter the critical section. So pi can't enter the critical section and it will execute this loop. It will check k is turned off. So whose turn it is? Turn is of k. So it will execute this code. So when it will execute this code, it will do flag of I equals to false. Okay. Then it will check this. While turn is not equal to I, turn is equals to k, which means turn is not equal to I. And this is a semicolon. Semicolon means we will have an infinite loop. Okay. So pi will execute this infinite loop. So pi falls into infinite loop. Okay. Now suppose that pj was executing critical section. Again pj is being executed. So what happens? pj executes this. Now what pj checks? Pj checks in place of I there would be j. So what pj checks? Pj checks if turn equals to j, then turn equals to k. Okay. So pj does this. If turn equals to j, then turn equals to k. Sorry, this is turn over here. If turn equals to j, then turn equals to k. So let's check whether turn is j. No, turn is not j. So it will not turn equals to k. So this statement is false. It won't do flag I equals to false and it will come out of the critical section. Okay, which means the turn will remain to k. This pj has executed, but still turn will remain to k. Okay, now what happens is that as turn is k, so pi will keep executing this infinite loop. As turn is still k, so it will check turn is not equal to j, turn is not equal to I, and it will keep executing this infinite loop. Which means, and when this infinite loop is getting overridden, this will get overridden when pk arrives and makes turn equals to I. But let us suppose pk doesn't arrive in the future. Then pi will keep executing this infinite loop. And thus, this condition, if there is a situation in which a waiting process can never enter a critical section, yes. Here, pi was the waiting process and it can't enter the critical section because turn equals to k and turn is not equal to I. Yes, there is a situation like this. Now, let us see the next part of the question. So, what this states? This states that if so, explain and suggest modifications to the code to solve this problem. Okay, so the problem arrived at this point. So how can we solve it? Okay, so we can solve it. Okay, we can write if flag of j, then make turn equals to j, and here if flag of k, then make turn equals to k. So that if a process wants to enter the critical section, we change it to their turn so that they won't be skipping this infinite loop. They will just skip this infinite loop and enter the critical section. So these are the modifications. If flag equals to j, then turn equals to j. If flag equals to k, then turn equals to k. And same modification would be applied for pj and pk code. This is the modification for pi code. Same you just need to change the variables. So this is the answer for this. First one is yes, second first part is yes, and second question second part, this is the modification in place of this code. This is a modification. This question belongs to the topic SQL from the subject database management system and was asked in GATE 1991. So the question states, suppose a database consists of the following relations. These are the four relations or the tables. Write a SQL program corresponding to the following queries. So let us first of all write what are the tables. We have supplier table with S code, S name and city. Then we have part table with P code, P name, P descending and city. Then we have projects table with project code, project name and project city. Then we have SPPR table with S code, P code, PR code and quantity. Okay. Now let us see what the question is asking for. So it is saying write SQL programs corresponding to the following queries. So query 1 is print P code values for parts supplied by any project in Delhi by a supplier in Delhi. Okay. So we need to print the P code values for parts which is supplied by any project in Delhi by a supplier in Delhi. It should be Delhi. Okay, so how can we do this? So let me write the SQL statement. So see, what you need to select. You need to select the P code. Select P code. From which table do you need to select P code? Where is P code? P code. P code is present in SPPR table. P code is present in and in which table we have part table P has P code and SPPR table. So we can select from any table. Let us select from SP table. SP table means let us select from this part table. Okay. So what we will write? We will write select P code. Okay. From. Now see here what you need to do. Here you need to find the parts which are supplied by project in Delhi by a supplier in Delhi. So you need to do the cross product, and cross product is done for which of the tables. So parts, we need to part table should be there as we need to find out what is the value of P code. So P code can be matched from part table as well as SPPR table. So we will do cross product for part table as well as SPPR table. And what we need to know, we need to also know what is the city, supplier city. So we also need to take this supplier into account for the cross product. So what we will do, we will do cross product for SPPR table. Let us rename it as SP table. Okay. For projects table, let us rename it as PR table, and from the supplier table, SU table. Okay. So supplier table is renamed as SU, projects table is renamed as PR, and SPPR table is renamed as SP table. Okay. Now let us see. We have select this So from which table we have to select? We have to select from SP table. We can select from SP table or from the part table, but as part table is not part of this, we can select from SPP table or SP table. From this where, now we have to write the where clause. So in where clause we need to give the equivalence conditions. So see, we are doing cross product of these three tables. So we need to make sure that this PR code is same. Here we have PR code and here we have PR code. So first of all, let us write that for PR code. So SP dot PR code should be equal to PR dot PR code. We have matched the PR code. Now, what else do we need to match? And here, let us see what are the common things. Okay, S code is there. See, here it is S code and here it is S code. So S code should be same, and SU dot S code should be equal to SP dot S code. And what is the condition? We need to make sure that the place is Delhi in both the tables. So which means PR dot PR city, PR dot PR city equals to Delhi, and SU dot city equals to Delhi. Now it will be perfect. It will give us the P code for the projects which are for values which are supplied by any project in Delhi by a supplier in Delhi. So this is the answer for part A. You write this as I will be clearing it up. Now let us see the second part of the question. So what the second part is asking for? Second part says print all triplets, which means we need to print city, P code as well as city, such that a supplier in the first city supplies to a specified part to a project in the second city, but do not print triplets in which city values are same. Okay. So what we need to do? We need to print the value of cities, P code as well as city, such that a supplier in this city supplies a part is being supplied from city 1 to a project in city 2, here a project in city 2, but these values shouldn't be same, which means it shouldn't be like Delhi, Delhi. It shouldn't be like this. It shouldn't be like this. We can have Delhi and Jaipur. It is allowed, but Delhi, Delhi is not allowed. Okay. So let us write the statement. So what we need to get? We need to get select city. We need to get city. So what is the first city? First city belongs to the supplier city. A supplier in the first city. Okay. Now we need to get the P code. So P code is present where? P code is present in SPPR table or SP table, as well as it is present in PR code. P code as well as SPPR table and part table. We are not using the part table, so we will take it from SP table. So here we will have SP dot P code. And we need to get the second city. What is the second city? A specified by to a project in second city. So from the project we will get the project city. So from PR dot PR city. So we have got these three values. Now we need to give the condition on which the tables on which the condition cross product needs to be done. So cross product needs to be done on the three tables only. Supplier renamed as SU, projects renamed as PR, and SPPR renamed as SP. Okay, these three we will this one as this one we will do the cross product. Why these three? Because here we need to get the city from those two, and we need to match the P code. We need to match the P code to C. Here we need to get the city from this as well as this, and we need this to get the PR code or the P code, you can say. Now let us see what we need to do. We need to write the where condition. Where. So in where condition, we just match the common things or the conditional things. So here, first of all, what we will do? We will do SU dot S code is equals to sp dot s code. SU and SP both has this S code, so they should match. Now what we will do? Now we will match PR dot PR code is equals to SP dot PR code. Both has PR code, SP as well as PR. PR and SP both has this PR code. PR code is present in both. So we need to match these two. And then we will write the condition from city and to city both shouldn't be equal. So we have sc.city shouldn't be equal, has this symbol in SQL, shouldn't be equal to pr.prcity. So here this is our SQL query for option A, second part. Now I would be clearing this out. Okay. Now let us see what is the part B. So part B states, write algebraic solution to the following. Get S code values for suppliers which supply to both projects PR1 and PR2. Okay. So we have some suppliers. So we need to tell them what is the S code value for suppliers who supply to two projects PR1 and PR2. They should supply to both the projects, not to one, to both projects. Like if we have supplier S1, we supply to PR1 but not PR2. We have S2, we supply only to PR2, and we have S3, we supply to PR1 and S3 to PR2. Then we need to tell only S3, as S1 do not supply to PR2 and S2 do not supply to PR1. So here how we will write is that, suppose first of all we will do the selection statements. First of all we will select based on project name. We need to select PR1 or PR2 equals to PR1 or project name equals to PR2. We need to select it from which table we need to select. We need to select from projects table. So we will get the entries where we have PR1 or PR2 as the project name. Okay. Now what we will do, this is a select statement. Now here we will project PR code. We will just get the PR code from those projects. So we get the PR code for these corresponding PR1 and PR2 projects. Okay. Now we have a divide statement. So suppose if we do A over some projections divides B over some projections. So it will find out the values of A which are related to all B. So here as we have both PR1 and PR2 projects, so we can use the divide statement. Let me first write it and explain it to you. So here we will have S code as well as PR code from the table SPPR. Okay, now I will explain it. So here we will have P code values for PR1 as well as PR2 projects. Okay, and if we have divide statement, then the output, this PR code as well as PR code will get cancelled out and we will get only S code values. We will get S code values for the suppliers A which is related to all B. So which supplies in both PR1 as well as the PR2 projects. So here we will get the supplier code for those suppliers. Okay. So here first of all this one will have just two entries. One for PR1 and its corresponding code, and we will have PR2 and its corresponding code. And here we will find out the supplier code for the suppliers who supply to both PR1 as well as PR2 using this divide statement. Okay. Now let us see option B. Option B part 2. So option B part 2 states, get PR code values for projects supplied by at least one supplier not in the same city. Okay. So here what we will do, we will first take supplier, do natural join. So what is natural join? Natural join is done on the common attributes. We will do natural join with SPPR. So if we do supplier with SPPR, then what is the common attribute? It is S code. So we will have only one S code entry, one S name, one S city, one PR code, one P code. Let me tell you over here, supplier as well as SPPR. Okay. So we will have one S code entry which is merged for both. we will have S name entry, city entry, P code entry, PR code entry, and quantity entry. This S code will be merged with this, and we will have the common S code entries only. Now we will do natural join of this with our projects table. Projects table. So what we have in projects, so again it is natural join, which means this PR code will be matched with this PR code. And PR name, do we have a PR name? No. Do we have a PR city? No. So this PR code will be matched and this S code will be matched. Which means just we can also do the cross product and write the where condition, but here we can also do the natural join. Now what we need to check by at least one supplier not in the same city. Okay, so we need to select ones in which the city is not same. City is not equal to PR city, which means supplier city is not equal to the project city. These two are not equal, we will get those entries. Now what we need to get? We need to get the PR code values. So we will project the PR code values. So this is part B, option 2 answer. So we have done all fours. This is the answer for this question. This question belongs to data structure subject and was asked in GATE CSE 1991. So the question states, consider a binary tree in the figure below. So we have been given a binary tree. Now we need to tell what structure is represented by the binary tree. Okay. So first of all, let me tell you what is a binary tree. A binary tree is a tree in which every node has at most two children. So see, here this node has two children, this node has two children, this node has one children, this node has zero children. So we have at most two children, every node has at most two children. So it is a binary tree. Now there can be various types of binary tree. First one is binary search tree, in which it is used for searching. As if we have a node X, then on the left everything less than X will be present, and on the right everything greater than X will be present. Then we can have heaps. Heaps can be either a min heap or a max heap, and we can have an AVL tree. AVL tree is a height balance tree, or we can have various other types of binary tree too, but these are common types. Now let us see what is this. Here we can easily observe that 1 is the minimum among all the values, yes. 5 is the minimum among this subtree, yes. 7 is the minimum among this subtree, yes. 13 is the minimum in this subtree, yes. 18 is the minimum in this subtree. 25 is the minimum in this subtree. Thus, we can easily conclude that we are having the minimum value on the top, and all the items which are below this are greater than, if this is X, all the items are greater than X in its subtree. Thus, we can see that it is a min heap. So this binary tree is a min heap. Okay. Now, let us see what is option B. So, option B says that give different steps for deleting the node with key 5 so that the structure is preserved. Okay, before doing this, let me tell you option C. As based on option C, we can easily solve option B. So option C says outline a procedure in pseudocode to delete a arbitrary node from such a binary tree with n nodes that preserve the structures. What is the worst case time complexity? So it is basically asking us to write the pseudocode to delete an arbitrary node from a min heap. So how can we do this? So if we want to delete a particular node, so the step is, first of all, find that node. Find that node index. Actually, these are basically stored in an array. So it would be stored something like this: 1, 5, 18, 7, 13, 25, 20, then it would be 11, 9, 15, 17, 27. So we need to basically, if we are given a node value like 25, we need to find the index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We need to find the index. So what's the complexity for finding the index? Either it can be order of n if we are not given the index, and if we are given the index, then there is no need of doing this step, so it will be order of 1. After we have found that index, let us suppose we want to delete 5. Then what we do is that replace node with last node, or we can write here replace desired node with the last node. Let us suppose here we need to delete 5, so we will replace 5 with 27. Okay, then what we will do, we will just to delete desired node. So here now we will delete this 5. We will just remove this link. Now what we will do? We will do down heapify from desired node index. So which means from this index where 5 was present, from index 1 we will do down heapify. So how we will do down heapify? So in down heapify we will basically compare this with its left subtree and right subtree and move the minimum among the two up, swap it. Like minimum among 7 and 13 is 7. So we will swap 7 and 27. Now minimum among its children, which means minimum among 9 and 11 is 9. So we will swap 9 and 27. So this is the tree for option B. So the structure is preserved, and this is the pseudocode down heapify. Now let us see the complexity. So we have done option A, the structure is min heap. We have deleted 5, and this is the output node after deletion. And the procedure, pseudocode, this is the pseudocode for option C. Now we need to tell the worst case complexity. Okay. For down heapify, what we are doing is that we are just checking through the height of the tree. So its complexity would be order of log n. Why log n? Log n because heaps are almost complete binary tree. Almost complete binary tree means all the levels will be completely filled except last level, and that too is filled from left to right. Okay, so its height is log n. Height of almost complete binary tree is log n, which means height of heap is log n. And if as we are searching in the height during heapify, so its complexity would be order of log n. So what is the total complexity? There can be two cases. If we are given just the value, like we have to delete, let us suppose 11, then we need to find 11. Complexity of finding 11 would be order of n. Then heapify complexity would be order of log n. So its complexity would be order of n. And if we are given an index, let us suppose index 3, then no need to find it. Then finding complexity would be order of 1, and heapify would be order of log n. So it would be order of log n. As here in this question we are given that an arbitrary node. So we can assume that we are just given a value and not an index. And here the replacing complexity is order of 1, can be neglected. Deleting complexity is order of 1, can be neglected. So the answer for this is order of n, or we can say if we are given an index, then order of log n. This is the tree for option 2, and min heap is the answer for option 1. This question belongs to the subject engineering mathematics and was asked in GATE 1991. So the question states, show that the product of least common multiple and the greatest common divisor of two positive integers a and b is a into b. Let us solve first part A. So what is least common multiple? It is LCM. So the least common multiple, let us suppose if we are finding LCM of 10 and 15. So the multiples of 10 can be 10 into 1 is 10, 10 into 2 is 20, 10 into 3 is 30, 10 into 4 is 40, and so on. 15 multiples are 15 into 1 is 15, 15 into 2 is 30, 15 into 3 is 45. So here we can see 10 is not present over here, 20 is not present, but 30 is the least common multiple. Okay. Now what is greatest common divisor? The divisors of 10 and 15. So the divisors of 10 are 1 is a divisor, 2, let us start from 2. 2 is a divisor, 5 is a divisor, and 10 is a divisor. 1 is also a divisor. So we have 1, 2, 5 and 10. And for 15 they are 1 is a divisor, 3 is a divisor, 5 is a divisor, 15 is a divisor. So greatest common divisor, let us start from the back. 10 is not present over here, but 5 is present in both. So 5 is the GCD and 30 is the LCM. Now let us solve this question. So the question is saying if we are having two numbers, then we need to prove that LCM of A and B when multiplied by GCD of A and B, then it is equals to A into B. As in the previous example, for 10 and 15, the LCM was 30 and GCD was 5. And what is 15 into 10 is 150. And 30 into 5 is 150. So 150 equals to 150. So we need to basically prove this. Okay. So how can we prove? So assume that we are having two numbers A and B. Now let GCD of A and B be given by D, and let LCM. So if A and B have GCD as D, then can we write F to be A divided by D? See, if we are having a number A and its GCD is D, GCD is D means it is a multiple. So D will obviously divide A and F will be that factor. And we can write F equals to AD. We can write A equals to DF. Okay. Now let us suppose that if we can write it like this, then we can also write G equals to B by D. See, if the GCD of B is D, then definitely D will have some factor. Let us suppose it to be B. D will have some factor which is G, by which D can divide B. See, in this example what happened was, in 10 and 15 its GCD was 5. So what is that factor? That factor is 15 by 5, that is 3. So here this is G, this is B and this is D. So the same we have written over here, and we can rewrite this statement as B equals to GD. Okay, so we got these two statements. Now let us suppose that the LCM, this is for the GCD part. Now let us suppose that the LCM of A and B is C. Okay, now we know that the LCM is C. So LCM has to be divisible by A. See, if it is a multiple of A, see, this is a multiple. C is a multiple of A. So C is divisible by A, C is divisible by A. Okay, and we can rewrite this as C is divisible by A and B both. C is divisible by, what is the value for A? DF. C is divisible by DF, and what is the value of B? GD. Okay, so C is divisible by DF as well as GD. Now see, here observe one thing. You can easily see that F and G will do not have any other common factor. Why? Because let us suppose F and G had some common factor as 2. Let us suppose F was 6 and G was 8. Then they have a common factor as 2. It won't be possible, because if they had a common factor as 2, then that common factor will get shifted over here to the D, and D would be having a larger value because this is the greatest common divisor. So that 2 will become part of the D. So we can easily say that F and G won't have any other common factors. Otherwise D would have been bigger by that factors. So we can write C as D into F into G. Okay, C can be written as D into F into G. It is the smallest possible number. Why? Because we cannot have a common factor among D and G and this. We cannot have a common factor among F and G, and D is the GCD and F is the and C is the LCM. So LCM can be written as D into F into G. It is the smallest number. Now see this statement. Now we have to prove that A into B equals to LCM into GCD. Okay, so A into B. We can write A value to be equals to D into F. Yes. We can write B value equals to G into D. Yes. Now let us take D over here and D into F into G over here. D. And what is the value of D into F into G? It is equals to C. So what is this D? D was equals to our GCD. And what is this C? It was equal to LCM. So we have proved that LCM into GCD equals to the product of the number. So we have basically proved this statement. Okay. Now we will see the statement B. But first of all, let me clear this stuff out. Okay. So what is our option B? So option B is saying, consider the following first order formula. Okay. For all x, there exists a y such that Rxy. Okay. Which means if we have an x, then definitely we will have an y such that x will be related to y. Which means for all x, if we have a x1, we will have a y for it. If we have a x2, we will have a y for it. They may have a common y. If we have a x3, we will have a y for it. We will have a y for it. Okay. Let us try to break it down in the form of a graph. It will be more easier. So what it means, if for all x there exists a y, it means for every node there will be an outgoing edge. For every node there will be an outgoing edge, which means it will be related to something. Okay. Now let us see option B. For all x, for all y, if Rxy exists, then Ryx do not exist. Okay. So what it means in terms of graph, if we have an edge from A to B, then it means that we can't have an edge from B to A. Okay, if there is a directed edge from A to B, then we can't have an edge from B to A. This is the anti-asymmetric property. This is the asymmetric property, which means if we have an edge from over here to here, then this implies that we can't have an edge from here to here. Let us name this as A and B. If we have an edge from A to B, then we can't have an edge from B to A. Okay. Now let us see this option. For all x, for all y, for all z, if Rxy exists and Ryz exists, which means if we have an edge from A to B, or if x is related to y and y is related to z, which means we have an edge from B to C, then we will have an edge from A to C, or we can say Rx is related to z. This is called the transitive property. Okay. Yeah, which means if we have an edge from over here to here and from here to here, then it means we will also have an edge from here to here. Let us rename that A, B and C. If AB has an edge, BC has an edge, then AC will also have an edge. Now let us see option D. Option part D. Part D is for all x. X is not related to x, which means in terms of the vertex, we can see we cannot have a self loop. No self loops. Or we can say irreflexive relation. Okay. Now we can easily see that we cannot have a graph with all these properties. Let us try to generate one. Let us take 3 vertices. Okay. See, every vertex must have an outgoing edge, so this must have an edge, this must have an edge, and this must have an edge. We can't have edge to the same vertex, so they must go to some other vertex. Let us suppose from A it goes to B. Okay. Now B can't have an S to A because of this second property. So B will definitely have an S to C. Perfect. Now C can't have an S to C because of this irreflexive property. C can't have an S to B because of this anti-asymmetric property. C can't have an S to A because of asymmetric property. So this is not possible. So we can't have a graph like this. Let us try to also prove this with the help of a contradiction. Okay. So we will assume that, let us suppose we have a structure S with V vertices and E edges such that the cardinality set of V is N, which means we have a graph. In terms of graph, we have a graph S with N vertices. Let us assume, and it follows all these properties. Okay, now we have to prove that this is a contradiction, that it shouldn't be happening. Okay, so if we are having n vertices and n belongs to natural number, okay, so what we mean by property is, it means everyone should have an outgoing edge, so it means we should have n outgoing edges according to property 1. Okay, let us rename this as property A outgoing edge property, property B asymmetry property, property C transitive property, and property D irreflexive property. Okay, now see, since no symmetric edges are around, as it is having asymmetric property, okay, and no self loop was allowed due to this property D, which is the irreflexive property. Thus, by pigeonhole principle, we must have at least n cycles. We must have an n length cycle by the pigeonhole property principle. Okay. Now see, any transitive relation on n elements with an n cycle is an equivalence relation. This is a property. What is the property? The property is any transitive relation. See, this is a transitive relation. We have proved this. This is a transitive relation. Any transitive relation on n elements with n cycle. N cycle by pigeonhole principle. With n cycle must be an equivalence relation. What is the meaning of equivalence? It should be reflexive, it should be symmetric, and it should be transitive. Okay, but see, but this is not reflexive and not symmetric, it is only transitive. Thus this is a contradiction, like we cannot have a graph with n vertices which follow all these properties. So here we can easily say it cannot have a finite model, which means we cannot have a finite model following all these properties. All these properties cannot be followed by a finite model. No. Okay, it can be followed by an infinite model. Infinite model can follow. If an infinite model can follow, it means it is satisfiable. Not by a finite model, but by an infinite model. Okay, let us see an example. Okay, let us take the less than equal to relation. A relation Rxy is defined as x is less than 1, which means 1 will be related to 3 as 1 is less than 3, 3 will be related to 5 as 3 is less than 5. Okay, so everyone will be less than something, as we will have infinite as a larger number, so there will be definitely someone greater than every number, so property A is followed. If 3 is less than 5, then 5 can't be less than 3, so property second is followed. If 3 is less than 5 and 5 is less than 7, then 3 is less than 7 for sure. Thus transitive property is followed. 3 can't be less than 3, as it is not less than equal to, is strictly less than. So property D is followed. Thus we can have an infinite countable model, and this is the model. So it is satisfiable, we can have an infinite model, but we cannot have a finite model following it. This question belongs to theory of computational subject and was asked in GATE CSE 1991. So the question has two parts. So the first part is, given a number of, find the number of binary strings W of length 2n with the equal number of ones and zeros, and the property that every prefix of W has at least as many zeros at once. Okay, so we have binary string. Binary string means it will have either 0 and 1. Of the total length, we have a W string of total length 2n, such that it has equal number of ones and zeros, which means it will have n ones and it will have n zeros. Okay, and the property that every prefix of W has at least as many zeros at once. Okay, which means suppose we have a, is this allowed? Yes, as it has every prefix. This has 1 0 and 0 ones, so this is allowed. This is allowed as equal number of zeros and ones. Is this allowed? No, as it do not have equal number of zeros and ones. This is allowed, and every prefix has more zeros than ones. Is this allowed? Yes, equal number of zeros and ones, and every prefix has more zeros than ones. If you carefully observe this and you replace 0 by opening bracket and 1 by closing bracket, then you can easily see that it is nothing but a balanced parenthesis problem. Balanced parenthesis problem. So it is basically asking what are the number of ways in which we can create balanced parentheses out of total 2n parentheses, or n opening parentheses or n closing parentheses. So it is a standard problem equal to the nth Catalan number, which is equals to 2n cn divided by n plus 1. It is nth Catalan number, or it is equal to the Dick-Word problem. It is a standard problem in which we just replace 0 by x and 1 by y, and it is the same problem. So this Dick-Word problem or the balanced parenthesis problem or the given problem all are same, with the answer equal to nth Catalan number 2n divided by n plus 1. Now let us see option B. So option B is saying, show that all vertices in an undirected finite graph cannot have distinct degrees if the graph has at least two vertices. Okay. So which means number of vertices is definitely greater than 2. And let us suppose n equals to 10. And it is saying we cannot have distinct degrees. So what can be a degree? Degree can be 0, 1, 2, 3. Let us try to do it by contradiction. Okay, let us try to do it by contradiction and assume that all degrees are distinct. So we have degrees from, for n equals to 10, we have degrees from 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Which means for n, we have degrees from 0, 1, 2 up till n minus 1. Okay, now let us try to plot this graph. If we have 10 vertices, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we have a 0 degree vertex. Let us suppose this is a 0 degree vertex. So it won't be connected to anyone else. Yeah, and see, we have a 9 degree vertex too, which means it should be connected to everyone else. It should be connected over here, over here, over here, over here, and over here too. It should be connected to this too, which means we can't have a 0 degree vertex and a 9 degree vertex simultaneously. So we can't have a 0 degree and n minus 1 degree vertex simultaneously. For that to happen, two vertices should have same degree. Should have same degree. It also goes by the pigeonhole principle. You will get the same statement, like, which means all vertices cannot have distinct degrees. Thus, we have proved it that all vertices cannot have distinct degrees by contradiction. And thus, we can say that we can have 0 to n minus 1 degrees can be there, but two of them should have same degree, which means either two vertices with degree 2 or two vertices with degree 0. It is acceptable, but all distinct degrees are not acceptable. So the answer for first part is nth Catalan number, and here we have proved this. This question belongs to theory of computational subject and was asked in GATE 1991. So it has two parts. Let us see each of them one by one. So part A states, show that the Turing machines which have a read-only input tape and constant size work tape recognize precisely the size of regular language. So we have a read-write tape, but here it is restricted that it is a read-only tape. So write is restricted, and in normal Turing machines we have infinite tape, but here infinite is restricted to constant size tape. Like we will have some symbols which will represent the end delimiters, and we will have a read-write head over here and our logic over here. So the read-only Turing machine, so it is a read-only Turing machine, or we can say two-way Turing machine. It is basically also called 2DFA, two-way finite automata, or two-way or 2DFA. So it's basically a class of models of computability that behave like a standard Turing machine, and here it can move in both the directions of input, but it cannot write it. It can only read in this constrained input size, but cannot write it. Okay, so this machine is a bare form equivalent to a deterministic finite automata. So DFA is equivalent to 2DFA, which is equal to Turing machine with read-only constraint on a finite string. and thus its power equals to the DFA power. So what is the power of DFA? A DFA can parse only a regular language. Thus, a Turing machine with read-only can parse only regular languages. So this is the statement for the first part. Now let us see part B. So part B states that let L be the language of all binary strings in which the third symbol from the right is A1. Okay. Give a non-deterministic finite automata that recognizes L. How many states does the minimized equivalent deterministic finite automata have? Justify your answer briefly. Okay. So we have a binary string which means a 0 and 1 string in which the third symbol from right is A. Okay, so let us try to write the regular expression for it. So it can have any number of symbols, but the third symbol would be 1, and after that it can have either a 0 or 1, and after that a 0 or 1. Okay, so we need to draw the DFA for this. But first of all, let us draw the NFA, as NFA would be is much easier than drawing a DFA. So 0, comma 1, then a 1, then either a 0 or a 1 to this state, then either a 0 or a 1 to this state. Let us rename the states to be A, B, C, and D. Okay, so here D will be the final state. Yeah. Now let us convert this DFA to a NFA. Okay, so we will have on 0 transition and a 1 transition. Let us start with A. So A on a 0 goes to A. Okay, A on a 1 goes to either A or B. So we have A or B. What are the new states? A is already there, we have AB. AB on 0. So AB on 0 goes to A and C. AB on 0 goes to AC and AB on 1. So A on 1 goes to A or B and B on 1 goes to C. So we have ABC. So we have AC as new state and ABC as another new state. Okay, so AC on 0. So A on 0 goes to A, C on 0 goes to D. So we will have AD. AC on 1. So A on 1 goes to A and B and C on 1 goes to D. So we have AB and D. Now we have ABC. So what are the new states? We have AD as a new state and ABD as a new state. Okay. So ABC. ABC on 0. A on 0 goes to A. B on 0 goes to C. C on 0 goes to D. So we will have here ACD. ABC on 1. A on 1 goes to A on 1 also goes to B. B on 1 goes to C. C on 1 goes to D. So we will have here A, B, C and D. Now we will have new states A, C and D and A, B, C and D. Now AD on 0. A on 0 goes to A and D on 0 goes to nothing. So we'll just have A. AD on 1. So A on 1 goes to A and B and D on 1 goes to nothing. So we'll just have A and B. Now we have ABD. So ABD, A on 0 goes to A, B on 0 goes to C, C on 0 goes to D. So we will have ACD. Okay, A on 0 goes to A, B on 0 goes to C, and C on 0 goes to D. So we will have ACD. And ABD on 1. So A on 1 goes to A and B, and B on 1 goes to C, and C on 1 goes to D. Now we will have ACD. So A on 0 goes to A, C on 0 goes to D, D on 0 goes to nothing. ABCD. A on 0 goes to A, B on 0 goes to C, C on 0 goes to D, D on 0 goes to nothing. And here ACD on 1. A on 1 goes to A and B, C on 1 goes to D, D on 1 goes to nothing. Then we have ABCD. A on 1 goes to A and B, B on 1 goes to C, C on 1 goes to D. Okay. Are there any new states that are not covered? No. How many states are there? 1, 2, 3, 4, 5, 6, 7, 8. So we can draw the DFA for this. Let me clear this NFA out and draw the DFA. What are the final state? Final state is any state that is having D, as D was the final state in our DFA. So this is the final state, this is the final state, this is the final state, this is the final state. So we will have four final states. So let us draw it. We will have A, we will have AB, we will have AC, we will have AD. A on 0 goes to A on 1 goes to AB on 0 goes to AC, AB on 1 goes to ABC, okay. AC on 0 goes to AD, AC on 1 goes to ABD, okay. Then we have A and it goes to A and AB, it goes to AC and ABC, it goes to AD and ABD. ABC on 0 goes to ACD, it goes to ACD, on 0 it goes to ACD. ABC on 1 goes to ABCD, on 1 it goes to over here. AD on 0 goes to AD on 0 goes to AD on 1 goes to AB, okay, this is 0. ABD on 0 goes to ACD, on 0 it goes to ACD, over here. ABD on 1 goes to ABCD, ACD on 0 goes to AD, on 0 it goes over here to AD, ACD on 1 goes to ABD, so it comes over here on 1. ABCD on 0 goes to, on 1 it comes over here, and on 0 it goes to ACD. So this is our DFA. What are the final state? Any state with a D is a final state. We have four final states. If we try to minimize it, you can see we won't be able to minimize it. So we have 8 states, and this is a minimized DFA. So these are the answer to both the questions.